since the development of the city is also thanks to the presence of the university and to the relationship between the city of Rende and the university.
Stamattina ho letto un po' gli scopi dell'associazione e è interessante vedere come ci sono associazioni private che riescono ad aprire sedi in quasi tutti i paesi del mondo e a raggruppare oltre 500.000 scienziati e ricercatori di tutto il mondo.
This morning I take a look about the IEEE and I was very surprised as it is possible that a society can collect about 500,000 of scientists from all over the world.
Con lo scopo, con le loro ricerche, di migliorare sempre di più la qualità della vita sul nostro pianeta. E facevo un paragone così vi lascio subito, che anche la politica dovrebbe prendere il meglio delle menti e degli scienziati, diciamo nel senso più politico, per camminare insieme, perché purtroppo molte volte la scienza va avanti, ma chi poi dovrebbe applicare oppure aiutare questi sforzi che si fanno da parte vostra è indietro, e il mio augurio è che la politica si doti anche di queste strutture dove poter camminare insieme, perché sono due mondi, due realtà che per avere un reale sviluppo del nostro pianeta devono purtroppo camminare insieme. Non ha senso gli sforzi che fate voi e se poi non vengono recepiti da chi dovrebbe applicarli. Io vi ringrazio per essere qui, vi auguro un buon lavoro e speriamo che da questi incontri nascano nuove realtà e nuove proposte per migliorare sempre di più il nostro ambiente, la qualità del lavoro, della vita, e fare qualcosa per i nostri giovani che purtroppo
Please say that the surprise is that the works of the scientists is devoted to ameliorate the life, our everyday life. And he said that it should be also the main aims of politicians. And one of the keys for this is the collaboration between scientist world and the politician worlds to collect the best mind to have the common goals to ameliorate our day life.
I miei genitori, nel mettermi al mondo circa 60 anni fa, avevano la certezza di darmi un mondo migliore del loro. Venivano dalle macerie del dopoguerra. Io purtroppo, io ho una figlia di 16 anni, questa certezza non ce l'ho ed è angosciante, sia come amministratore che come padre, non aver avuto questa certezza, e quindi penso che tutte queste iniziative che vanno a sostegno delle nuove generazioni siano solo da sostenere e da applaudire. Grazie per la vostra presenza a Rende.
And he said that when he was young, his parents, they believe that they give him a better world. Now, as counselor, but also as dad, as father, is not so sure that he is giving to his daughter a better world. So he thanked all us to be here and to work together to make a better world. Thank you. Thank you very much. Thank you. Please bring our greetings and our thanks to the measure of Rende. And for sure, from our side, we give our full availability for support case and for scientific our task. And now, please let me introduce Professor Fabrizio Di Maio. He is the delegate of the President of Engineering Order of Cosenza. Thank you to be here.
Thank you. It's with great pleasure that I bring you greetings from Engineering Order. I thank Professor La Monica for involving us in this conference, and therefore allowed us to contribute to this important workshop. Engineering and innovation works side by side, and this is more important for our culture, our life, and occasions like these are indispensable for moments for ground and confrontation, even from professional colleagues. I believe that perhaps never as in recent years have technology to support the living environment and buildings innovated, revolutionated in some cases. And metrology today is applied in living environment and building in many aspects of our life, perhaps more than we suppose. Building diagnostic systems, IoT, AI-based monitoring system, measurement system for BIM, digital twins is a more important aspect. And this aspect allow to achieve a standard in terms of efficiency and comfort that only sometimes, so far times, is not conceivable. We are very pleased that workshop will award the best work with an award named to Professor Grimaldi, professor of this university that always very close to our order, the initiative of our order. I thank you again for the invitation. I wish everyone good work.
Thank you very much. Thank you very much, Fabrizio. Also to mention Professor Grimaldi. Professor Grimaldi was my teacher, my magister. I say this in Latin because I think that it is the word that best summarizes what it was for me and for many students in this university. So I give this floor to Professor Stefano Curcio. Professor Stefano Curcio is here as the delegate of the rector to bring his greetings to us. He's very sorry. I've called him yesterday and unfortunately was busy and he cannot stay with us, but Professor Curcio is also my director, the director of the Department of Computer Science, Modeling, Electronic Systems. So, Stefano, please.
Thank you, Francesco. Ladies and gentlemen, good morning. Okay, I'm very happy to be here for this inaugural ceremony. Okay, as Francesco was saying, I am representing also the rector, Professor Leone, who is not present here just to for some institutional commitments, and also as the head of our department. I also would like to mention Professor Grimaldi, since he was unfortunately one of the pillars of our department, and I can imagine that he would have been very happy to be here today for such an important occasion. And okay, I had a very quick look to the scientific program, and I was actually impressed about all the topics that this Congress would like to face, to discuss, to set up a kind of scientific environment in which to discuss about new solutions for metrology, considering that this topic, you know much better than me, is involves many different scientific environment. I am also a chemical engineer, now borrowed to this institutional role, but in principle, I am a researcher of chemical engineer, and I know that having reliable instruments to interpret the complex processes which we study in our lab is very important, and I am really sure that at the end of this scientific meeting, we will have some new developments, some new information that can be used by the scientific community, considering that from this meeting we can actually embrace many different topics ranging from structural mechanics, from IoT systems, from computer science, also for chemical engineers. And before starting officially the meeting, I would like also to thank Professor La Monaca and Professor Carni, who has spent a lot of time in defining all the details which are the basis for a successful Congress. So I would like to thank you everyone, and unfortunately I have some other commitments. I have a lecture which starts in half hour, less than half hour, so I cannot attend all the speeches and all the meeting. I hope to be here in spot and some speeches, and have a pleasant stay here in the University of Calabria, and I wish you a successful Congress, and thank you for being here.
Thank you very much. Thank you for staying with us. Always. Thank you very much. So, before to start, please let me bring you the greetings from the President of the Calabria region, Dr. Roberto Chiuto, and the Vice President, Giuseppina Princi, so as the President of the Province of Cosenza, Dottoressa Rosaria Succurro, and the Prefect of Cosenza. They wish us good work, and thank you all to be here in this workshop. Thank you. So, we are starting the first IEEE International Workshop on Metrology for Living Environment. The Metrolive ENV organization was a complex task due to the large and increasing interest of our research and application areas. Efforts from many people were required to shape the technical program, arrange accommodation, manage the administrative aspects, and set up the social functions. We wish to thank all and each of them. This workshop was improved by adding a significant number of special sessions for two reasons. So many are the application fields of the metrology for living environment that a single track could have been too much dispersive. In spite of a centralized research address definition, a spontaneous aggregation of well-focused teams has been gathered, with specific aim of providing a forum of specific debate very close to the single research field. We wish to thank the organizers of these special sessions for their cooperation and support to the workshop organization. The technical program was particularly difficult to be arranged, since we received for this workshop 78 abstracts from all over the world. Due to the time limits of the conference, only 59 papers have been selected after a review activity of the program committee and additional reviewers. We'd like to thank all people who contributed to this process with opinions, comments, and suggestions to choose the best papers and even improve their quality. 60 countries are involved in Metrolive ENV. Chile, China, Czech Republic, Germany, Ecuador, Ethiopia, France, Great Britain, Greece, Italy, Japan, Philippines, Poland, Russia, Spain, and United States of America. The technical program includes several events and activities. The keynote speeches will be held by experts in the field of metrology for living environment. Vasilis Charosis, School of Civil Engineering, University of Leeds, that will have a speech on structural inspection and assessment of our aging masonry infrastructure stock. And Professor Alberto De Capua from University of Mediterranea di Reggio Calabria, that will have a speech entitled Design After COVID-19, Strategies for the Evaluation, Monitoring and Control of Indoor Air Quality. This workshop included a half day of tutorials. Lucia Figuli, University of Zilina, that have a speech entitled The Measurement of Blast Wave Propagation and Evaluation of Structural Resistance Under the Blast Load. And Dr. Stefano Loretti of this university, University of Calabria, that have a speech entitled Passive and Active Infrared Thermography, Live Comparison of Cutting-Edge Excitation Strategies and Post-Processing for Investigating Masonry Materials and Wood Samples. Moreover, 4 journals, international journals, are in touch with us, and we have organized the special sessions on them: Sensors, Buildings, Comunicatie, and Acta Imeco. So, selected paper will be invited to submit extended version of the paper to these journals. I would like to thank all the editor-in-chiefs to give us this opportunity and to trust to believe in our research. This thanks to our sponsors, we had many awards. The first one, the Best Conference Paper Award, entitled to Professor Domenico Grimaldi, that whose passion, enthusiasm, and commitment for science will be of inspiration for all the recipients of this prize. And this award is sponsored by Alma Software. The chief of Alma Software, Dr. Andrea Aiello, was also a student of Professor Grimaldi. So I'm very glad that he would support this prize. Then we had the second and third classified Best Paper Award that is supported by MDPI Buildings Journal, and the best paper presented by a young researcher supported by MDPI Sensors Journal. Then we have the best paper presented by a woman supported by the Italy section of Women in Engineering Affinity Group of the IEEE and by the Gibertini Balance, SRL. Best standardization paper that is supported by the CHEI Technical Committee. Thank you to all of them. Now some practical aspects. The workshop is hosted by the Conference Center of University of Calabria. On the ground floor, you are in the reception and the Aula Magna. Aula Magna entitled to Beniamino Andreatta. There are also the exhibitions and poster plays. On the first floor, you will find a Sala A and the Sala Stampa. On the program, you will see the place where your session will be. In the garden on the back, there is the coffee break and the light lunch place. The welcome party was held in Bar Colosseo. Thank you to all the attendees for a very nice evening all together yesterday. Thank you very much. We are glad to announce that the gala dinner will be held in Cuoco e Fiamme restaurant. You see in the slide the address. This evening we are organizing some buses that will pick up you in front of Marconi Hotel and will bring to the restaurant. So, thank you. We like also to thank the public and the private organizations for their patronage. The City of Cosenza, the City of Rente, Provincia di Cosenza, the Calabria region, the Ordine of Engineer of Cosenza, i campus Politecnico di Milano, University of Zilina, University Technic of Cluj-Napoca, University Politecnica delle Marche, i BIMI, the Italian Electrotechnical Committee, IET, ARPACAL, ARPA Puglia, ARPA Lazio, the part of the measure of Calabria region, the Italian group of electrical and electronic measurements, and the Italian group of mechanical and thermal measurements. Thank you all. And we like also to thank the public and private organizations that supported the meeting in different ways. Obviously, the Department of DIMES, Department of Computer Science, Modeling, Electronic and Systems, H Software, Alma, Gibertini, Conforti, Distec, Feudo Liguori, Magnolio, Integrated Logistic Support Engineering, DefTech, Sensors and Building. Thank you. A special thanks to Athena to support this conference continuously in a very professional manners, and is following us plus or minus in science 1 year. A special thanks to the University of Calabria and to the Department of Computer Science, Modeling, Electronic Systems for supporting and hosting the workshop. Finally, let us thank each of you for attending the first IEEE International Workshop on Metrology for Living Environment. Thanks in the name of all the organization committee. Thank you.
So I think that it's my honor to start officially the meeting and have a nice scientific workshop and pleasant stay here in University of Calabria. Thank you. And I think that there's the coffee break outside, no? Okay. Not yet. Okay.
Start with this. Yes, we can start with go ahead with the program. So we can start with the plenary lecture by Professor Sarosis. So first of all, a presentation of the speaker. Professor Sarosis is associate professor at the University of Leeds. He's an old friend of mine. He is an expert of measuring, modeling, and experimentation. Is in particular an expert of measurements of aging of structures and infrastructures made by measuring, and also on advanced numerical modeling, mainly using the distinct element method. So today, Professor Sarosis will speak about the structural inspection and assessment of our aging measuring infrastructure stock. Please, Vasilis, when you are ready, then the floor is yours, and you can start with your plenary.
Good morning, everyone. Thank you very much, Gabriele, for the introduction. Thank you very much, Francesco, for the invitation. It's such a pleasure to be here with you today. So, as Gabriele mentioned, today I'm going to give you a brief overview of the work that we did on structural inspection and assessment of our aging infrastructure. I will specifically cover three topics. Firstly, I'll speak about masonry in challenging environments. So I will try to state the problem, and then I will bring some examples from the past research that we did while I was at Leeds University, and I will finish off with some future directions. Some background information is always humanity, so to cover barriers and challenges and create opportunities. So we are like from urban centers to the space, or from remote corners of Earth to the depths of the ocean. So the US National Academy, with the input from people around the world, has identified a series of challenges, global challenges. And as you can see, one of them, number 7, is about to restore and improve urban infrastructure. And us as engineers, or as human, as a society, we need to do something to improve our urban infrastructure, and I will explain the reason why. But before I do that, I will just define briefly, what is infrastructure and how I define it. So I define infrastructure as the combination of fundamental systems that support our society. And you can see here different sectors of infrastructure that these range from transport to energy to water to communications. So it's not just the civil infrastructure, but is more like a network that interconnects together. So it is highly important and essential to maintain and restore our urban infrastructure, because this could support economic growth and productivity, and promote as well our social well-being. However, as you can imagine, our infrastructure is vulnerable, so it is aging and decaying over time. Why this is happening is because we are using it. So from the time that you are install something, it starts the decay process. So the cost of replacing and repairing is quite high. Also, our infrastructure is vulnerable due to short-term hazard as well as long-term change, such as climate change. So when I say some short-term hazards, this can be like due to like potential natural disasters like flooding, earthquake, but also due to induced, man-induced reasons like induced seismicity, for example, or accidental damage, or in other cases, terrorist attack. Something that we need to bear in mind is that our infrastructure is interdependent. And what I say by that failure at one sector can have an impact in another. And I have here some images to demonstrate that. For example, you can see here in the picture in the middle, you have like a burst water main in Boston in 2003. So because of this burst of the pipeline, people were not able to have water, but also the road collapsed. So it's not only that they didn't have water, but also they couldn't move from one place to the other. So it's like disturbance to the society. Same happened also in UK in 2007 when an electricity substation flooded, as you can see here. So people didn't have electricity, but also their houses were flooded. So it is important to take into consideration this interdependence and the effect of it. So how we can contribute into that? So we are facing the challenge not only to repair the infrastructure, but perhaps to restore it with systems that will allow to continuously improve it. Yeah. So this is a major, challenge that we are facing. So for example, you have a structure or something that is connected with bolts. So if you replace a bolt that has failed with the same exactly fault, you are not doing much. But if you are replacing with a bolt that is a smart bolt, it can tell you when it's going to fail, then you are providing some added value to that. And this is how we have to think for the future. This is the only way how to think for the future. So The main construction and infrastructure needs to be optimized, needs to be resilient, robust, and adaptable, and innovative across all sectors. And this is not an easy task that we have to undertake as engineers. So we require a multidisciplinary approach in order to face these challenges and tackle these problems. And this multidisciplinary approach is what this conference is all about. Yes, we have like people from different sectors here, from mechanical engineering, electronic engineering, civil engineering, and as mentioned before, you know, even politicians needs to be involved in this multidisciplinary aspect, because these are the ones that they have the problems, and us engineers will try to tackle and solve them. So some examples that I would like to bring here. This is like a
rescue missions underway after an arch bridge collapsed in Taiwan.
This is like a bridge that collapsed in Taiwan. This is the Namfang Ao Bridge. Several people killed, and others have been wounded. You can see here some snaps. What I want to show you here, what I want to highlight, that everything happened very fast. Here, there was a lorry here crossing the bridge. You can see the lorry crossing the bridge. So the bridge was operational, yes, and then suddenly happened. And this is something alarming for us, yes, that we don't have like a warning that something is going to happen. Well, engineers maybe have, but you know, politicians or others don't have a warning. So it's a way that politician needs to listen to engineers, and engineers needs to listen to politicians, because sometimes accidents can happen, you know, suddenly. This is another example I'm bringing here. This is a masonry arch bridge that so this is in fact live. Okay, thank you. So in fact, this is a live footage from the Greek news. To be honest, they are describing about the flood that happened in Crete at that time. So this is like a two-span bridge with a pier in the middle. You can see the pier here in the middle. So while the footage was going on, and you can see the water, we had like scour of the middle abutment, the middle support, which eventually led to collapse live on TV, which is, again, something that happened immediately and without any major warning. You can see the collapse here is happening here. So it is devastating, the event. So currently now there are actions to restore this bridge, and people are trying, divers are trying to collect materials from the bridge that collapsed and try to do the reconstruction. But yeah, so climate change is happening, and is an effect that we need to think about it and take care. So for us, the engineers, is extremely important to understand the asset life. Yes. So I have here a diagram, and the diagram shows, it has two axes actually. You can see here the capacity, and you can see the time here. So the capacity is the capacity of our infrastructure. Let's say, for example, in this case, of a bridge. So you have the required capacity. So this is the capacity that required when you are designing the bridge. So you can see it has like a straight line. Let's say, for example, is, I don't know, like 1,000 kilonewton capacity. And at some point, the capacity increases. You can see here the jump that because of more trains are passing the bridge, or heavier trains are passing the bridge, the capacity is increasing. And then you have the provided capacity here. And the provided capacity is the capacity of the bridge itself. And as mentioned before, the bridge, from the start, it starts to deteriorate, and that's why you can see that the capacity reduces. So we are losing capacity with time. So for us engineers, it's extremely important to identify this zero spare capacity point. So this is the point at which the provided capacity is equal to the required capacity. once we know this point, then we can avoid collapse. So how we can identify this point, this is a challenge, and also part of this conference, again, can try to address that, how we can develop early warning systems, or how we can better understand the condition of our structures or of our infrastructure, how they decayed, and how the required capacity will affect this decay. This is another example that I'm trying to bring here. So the required capacity can suddenly increase also because of demands of our society. And you see that the provided capacity is decreasing quite rapidly here. Because it's decreasing, it's quite steep, the line. Then we decide to strengthen that. So we increase the capacity. But again, what is this point here? This is like critical. So for us engineers, it's important to understand what is like the capacity that we have reached after we strengthen the bridge. And then deterioration is occurring, and again is important, this zero spare point here. So now going to masonry infrastructure. So it is clear that masonry infrastructure, when I say masonry infrastructure, I mean infrastructure related to bridges, masonry arch bridges. It can be tunnels, viaducts, or structures of architectural heritage even. So we have many of them, yes, especially in Italy, in Europe. We have many masonry arch bridges. In UK also. We have more or less 1 million spans of masonry arch bridges globally. So most of them are old, and they are subjected to significant signs of distress. Their aesthetic and heritage value of masonry infrastructure is significant, so sometimes it's difficult to do interventions in them. We also have weathering and sometimes increase of demands like axle loads for the trains, or flood events due to climate change that introduce some uncertainty in their long-term behavior. We don't know for how long they can last, how long, when we need maintenance of them. And such infrastructure is important for the economy and society. So, for example, we have like railway masonry arch bridges are more than 24,000 spans in UK. So if you want to replace all of them, you will have to spend more than 20 billion pounds. So there is an increasing need to better understand the life expectancy of our aging infrastructure and understand their long-term impact on network resilience. With respect to monitoring of masonry infrastructure, again, this is a difficult task. So far, what is happening is inspection and monitoring is happening using visual means or manual procedures. Usually you go there, you can see some typical examples of how we do inspection, either with ropes, or you have a cherry picker here where someone is studying and observing. Sometimes he's taking some images with a camera. But usually so far what is happening is a manual procedure. You're using like a hammer, you tap the hammer, and based on the sound, again, you can understand, whether there is hollow or there is solid brick behind. So I would say that it is time consuming, requires a lot of health and safety, depending on which country you are, but also is very subjective, yes? So you have an engineer that goes, takes some measurements, some snaps. He may think that one area is good, the other one is not. So if you bring 10 engineers, I'm sure that they will not give you exactly the same answer. Also, so far, the focus of the infrastructure was on the ultimate limit state. So as engineers, civil engineers, we were focusing a lot on at which load, above which load my infrastructure, my bridge would collapse, but not so much at what was happening at the service load, as we say. So in the service condition, so at the load in which some deformation occurring before the bridge has collapsed, before the infrastructure is collapsed. This limit, we call it more or less the permissible limit state, and how this increases over time. So there is currently no reliable method of predicting actually the long-term behavior of as-is masonry infrastructure. And when I say as-is masonry infrastructure, I mean the infrastructure that has already deteriorated. There are already some damages in it. So usually what we do is we observe, so we understand, we only take actions after an event has occurred. If we have like some major damages or even collapse, unfortunate collapse, then we can take some actions. But the idea is now to prevent that happening. So based on this philosophy, I have developed this masonry infrastructure research group at Leeds University. So the vision is to lead, innovate, and collaborate to maximize the impact of engineering on global challenges. So we're using a multidisciplinary approach to understand, quantify the rate of degradation of our aging infrastructure. And we are focusing on these four main areas: the inspection and documentation, advanced numerical modeling, repair, strengthening, and smart monitoring. So I'll try to speak today about these two, the inspection and documentation and advanced computational modeling. But before I do that, I understand that you are from a mixed background here, so I would like to introduce you about some basic principles of masonry structures. So one of the oldest building materials, so masonry is one of the oldest building material and proven to be simple and durable. So masonry structures are composed of masonry units, can be like bricks or stones placed one on top of each other, sometimes with mortar or without mortar. So it's very simple to construct, but you will realize if you go deeper to investigate that their mechanical behavior is complex. Yes, is a composite material. So it is complex. So it is brittle, so failure can happen suddenly. An anisotropic material, not isotropic like steel, for example. And mortar acts, so masonry is strong in compression and weak in tension. So you have the mortar that acts as a plane of weakness. There is a mistake here. This is mortar. This is masonry, not mortar. So mortar is acts as a place of weakness. So for existing or historic infrastructure, we mainly have failure occurring at the mortar rather than the bricks. So the bricks are much stronger than the mortar in most cases. So when you are applying low levels of stress, the behavior is linear elastic. However, the behavior is highly nonlinear after the formation of first crack and redistribution of stresses in it. So also another issue that needs to be considered is that masonry structures are characterized by complex geometric nonlinearity. Something that adds even more the complexity on understanding masonry structures involves the materials that it composed itself. For example, the masonry units, we have like can be stone that is completely irregular, or you can have some regular patterns of bricks. But even the stone characteristics or the brick characteristics can change. So never one brick is exactly the same as the brick next to it. So the strength may vary, not by a lot, but still, it can vary. Also, the mortar joint characteristics, the properties of mortar, again, they are variable, because you cannot construct an entire structure, an entire bridge, let's say, with the same mortar characteristic. You cannot assume that the characteristics have the same properties, yes? Also, you will find out that when you visit the site, that some areas of the bridge, for example, have been deteriorated more than some others. So again, that's, some critical factor here. Of course, curing process and the quality of the mason could vary. You can realize that if you are constructing a masonry arch bridge, or where they were constructing a masonry arch bridge, the workmanship, they were different, bricklayers. So each of them, they have a different workmanship skill. So the workmanship, again, can have a significant effect here. So I'm presenting a graph here where you can see the tensile bond strength of masonry during the construction and the moisture content of the bricks. So you can see if you try to have the same moisture content of the brick, the tensile strength, you can see the huge variation from 0.1 megapascal to 0.5. Yeah, so you can see the huge variation. So why I said all that? Because we are trying to perform some numerical modeling and understand. So we are trying to use mathematics, physics, and computer science and develop some advanced or high fidelity models sometimes to understand the behavior of masonry structures. And then based on the understanding of the behavior, then only we can take some decisions. So nowadays, with the increased computational power, simulations may take minutes rather than hours instead of days. So I have described how complex is masonry as a material, and I'll very simply, explain here that the way that you can model. So you can use the macro modeling approach, the micro modeling, and simplified micro modeling approach. So the macro modeling approach is an approach in which you smear the continuum, you homogenize. So you can see like a typical example when you have a large structure. You have you assume like a homogeneous material, and you can see phenomenologically where damages can occur. You have the micro modeling approach in which you are consider single bricks and mortar individually. So you can see an example here. Of course, we cannot do detailed micro modeling in a structure like that. It will take ages to simulate, and also it's very hard to define where exactly it's masonry unit is located and mortar. So usually we do this detailed micro modeling for experimental tests, let's say, for example, and then you have the simplified micro modeling in which the mortar joint is assumed as a zero thickness interface. So this is like a compromise between the two, and you have a simulation of the interaction of the blocks. Yes, so the zero thickness interface is representing that. And I have an example here. This is a video showing like a wall subjected to horizontal load at the top from the right to the left. So you can see like this is the macro modeling approach that the crack initiates and propagates more or less phenomenologically. We don't know how this is happening. Now, if you move into the simplified micro modeling approach, where you have zero thickness interface between masonry units, you can see more realistically where the crack is occurring, how it initiates and propagates. Yes. So this is like a distinction between the two approaches, the homogeneous and the simplified micro modeling. In simple terms, yes, I understand you are coming from different backgrounds. So this is what I did for my PhD, like some time ago. So I developed some numerical models able to simulate the behavior of masonry walls with openings in this case. So you can see here a wall with an opening. And I have used a simplified micro modeling approach. This is like a discrete element model where you have blocks, discrete blocks connected together with points, and you have some interaction with them. Of course, results have been compared with experimental testing. You can see some other examples here. So this research has been funded by Bersrold. It's a company that's specializing in masonry strengthening and repair. So something, of course, so I validate using a load displacement curve. So you have the load and the displacement at mid-span. But something that it came out from my PhD thesis was the difficulty for calibrating the numerical models. So these numerical models require a set of parameters that you have to input. And how you select these parameters is not an easy task, it's quite trivial. So for my PhD, I have used like an optimization strategy to do that. I will not go into that detail here, but I'm just, what I want to bring to you is that material properties are important, and identifying these material properties that you will feed into the numerical model is extremely challenging. So we have further, expanded on that and developed, different case studies. In this case, you can see like a simulation, a numerical simulation of the Bothwell vault. This is a church in Edinburgh. So the church was subjected to settlement. So we use, so we recorded the geometry more or less, to be honest, and we developed some scale models in the lab. We subjected them to different types of displacements and developed some numerical models. From that, we have developed a series of simulations using numerical models, and this is an advantage of the numerical model, that as long as you have it validated, then you can start playing with it and try different scenarios, what-if scenarios. So in this case, we tried different what-if scenarios, for example, uniform inward diagonal settlement. This is inward horizontal settlement, outward diagonal, different, and then you can see that you have different failure mode. So if an engineer goes to a structure and see a typical crack here, then you realize that probably this is due to inward diagonal settlement, and so on. So can give like an indication, you know, information about this crack and how originated. We also moved into arches. You can see here some arches, single span arches. So arch is a peculiar structure, acts in compression. So usually when you apply a load at quarter span, you have this typical 4-hinge mechanism that many of you that working on masonry structures are familiar. And we look also how subsidence also affect like a vertical movement of the vertical support, how this is influenced the failure mode here. You can see here with some spandrel walls and without spandrel walls. We also look at the masonry arch bridges apart from arches itself. So the idea was to try to understand how they behave. We have more than 60,000 masonry arch bridges in the UK, and many of them are more than 100 years old, deteriorating. So for us, it was important to understand how they behave, and we developed some numerical models. Mainly, we validated using large-scale field tests, also small-scale tests. So you can see here a simulation. So it is the arch ring with the soil, and mainly we focus in through 3 main things, yes. So the impact of the self-weight, the dispersal of the load from the live load, how the load disperses into the arch ring here, as well as the effect of the soil, the active and passive pressure of the soil, and how can this passive resistance can be mobilized. Another example that we worked on was on multi-ring masonry arch bridges. These bridges are quite peculiar with the term that, you know, they are composed of different layers of rings. That's why we call them multi-ring masonry arch bridges. You can see them here. A typical failure is delamination, as we call it, of the lower ring, and this is because of water leaching through the mortar joints and pushing this outwards. So while discussing with engineers in UK, we realized that what they are mainly doing is if they want to simulate a multi-ring arch bridge, is they are considering the thickness of the bridge entirely rather than simulating every single ring. To be honest, these rings, they have some shear failure occurring, so they can slide each other, which is quite critical. So we wanted to see how they simulate and what would happen if you simulate the ring as a solid or less or different bricks that have same thickness, and if you have a more realistic representation of the geometry of the bridge. And we find out that depending on the span of the bridge, you have such a high deviation, like this is I think 3 meter, 5 meter span. You can have like a variation of 75 and 180. So they are significantly underestimate, yes, the behavior of the arch in this case. And if you look with an arch with the soil, the deviation is smaller because you have the backfill material, the soil, which keeps the bridge in compression, but still you have like 20 to 25% deviation, which is quite interesting. So the point I would like to highlight here is that the geometry of the bridge is extremely important, yes. So sometimes engineers, we try to idealize, simplify things, but sometimes it's important not to idealize everything, and the geometry here plays a crucial role. So it is important to know what we are idealizing. To enhance this statement, I will bring also this slide here, which shows the behavior of skew arches. So I have started working on that like several years ago, 8 years ago, on skew arches, which again, they are very peculiar structures. So as you can see, there are three main methods of construction: the false skew, the helicoidal method, and logarithmic method. So these are methods of construction. So what engineers again are doing, sometimes they are assuming that the span of the bridge is the diagonal here, the skew. Just to define also what a skew arch is like an arch that spans an obstacle at an angle. Yes. So you have a river, so you don't cross it perpendicularly, but at an angle. Yeah. So you can see, let's say the river is in horizontal direction, and then you span. So the road is in this direction, diagonal. So you have an angle of skew based on that. So what engineers are doing there, they are assuming that the span of the arch is either in the diagonal, which is the longer direction, or even the vertical one. Yeah, they simplify. So again, if you try to simplify that, you will end up in different, solutions. And again, the geometry is playing a key role here. So I'm presenting here the load carrying capacity, normalized the load carrying capacity of the different methods of construction here, the helicoidal, logarithmic, and the false skew arch. So when you have the false skew arch, when you have zero angle of skew, so when it is rectangular, let's say, it is, let's say, is normalized 100% of my load. But as the angle of skew increases, you see that the load carrying capacity decreasing. So if an engineer is assuming that a skew arch, it has a regular dimensions, then underestimates the capacity. On the other hand, if you have the helicoidal and logarithmic, as the angle of skew increases, you have higher load carrying capacity. And the main reason for that is because of the construction method. For the false skew arch, you have the masonry units laid perpendicularly to the abutments, parallel to the abutments, sorry. So the hinge formation is like a straight line, while for the helicoidal, you have more like a zigzag pattern. And this zigzag pattern creates some shear resistance, yes, and can resist further load. So the geometry, again, is a crucial issue here. Of course, we are looking at flooding and how flooding is affecting. So this is a video from Spain, actually. So it's a bridge, but I wanted to highlight here, you have the flooding of a river. But what is important is not to consider just the bridge, because it's a system of systems. So you can see here a wall passing by and create like a strong wave that can create further damage to the bridge. So as engineers, it's important not to look at structures in isolation, but more or less what's happening around them, the upstream and downstream of the river. So holistic representation or simulation of these phenomena are extremely important for us to gain a better and more accurate result. Also, another topic that we have covered was that of the fatigue phenomena. So how masonry, at the moment, what is happening, how the engineers, at least in the UK, trying to understand or predict the load carrying capacity of masonry arch bridges is they develop like a numerical model, sometimes is a 2D, while masonry arch bridges behave in 3D. And what they are doing is they are applying a load at quarter span, because this is the worst case. The load is static, and based on that, they obtain the ultimate load carrying capacity, so the maximum load that the bridge can carry. However, this is not what is happening in reality. In reality, you have trains passing over a bridge, and you have some fatigue phenomena occurring. So I think there needs to be a shift somehow and move from what we are currently doing now into a condition-based assessment. For example, we know what sort of trains are passing over our bridges, what is the weight of these bridges, so we can more or less accurately predict, the load that is applied to this bridge. And we're trying to represent that, by a moving body here, equivalent weight by a moving body, and see the damage occurring into the bridge, which is in a way a more realistic phenomenon of what is happening. Quite a few in UK. Again, these are very tall, slender structures. Trains are passing by. I passed by this one, this viaduct more or less 2 weeks ago. It is an impressive viaduct on my way to Glasgow. So what is happening with these structures? They are tall, slender. They've been there for more than 100 years. So you can see some creep phenomena developing because of the weight of these structures. You have some creep phenomena. In general, when you have a masonry prism and you are subjected to vertical load, you have some biaxial tension occurring at the brick unit and triaxial compression. So the failure mechanism that occurs here is like a vertical crack. So what I have shown you so far in all my simulations are failure occurring at the brick to bricks, to the mortar itself, yes? I haven't shown you any failure to the brick. Why? Because mainly we have failure at the mortar because it's much weaker than the bricks. However, we have cases like that where failure can occur both in the brick and mortar itself. So what we have developed here 4 years ago is like a numerical model in which we have discretized the masonry units and the mortar, and you have more or less a clear representation of the fracture that is occurring, the vertical cracks that are occurring in our masonry. I'm very much also interested in, especially my group, interested in the behavior of old structures and how we can obtain, how we can be inspired from the way the master builders used to construct structures. I'll bring 2 examples here. This is like a helical staircase. This is from the San Domenico de Bonneval. It's a helical staircase. I think there are 128 steps. So it's quite high. So this is only one helix. It has 3 helix. So what is happening? It is a simply supported structure in a way. So you have a support from one part of the wall here, and the other one is resting to the flight, to the step below. So what is happening with this structure is quite tall, and the load is transmitted from the top. One would think actually that the load is transmitted from the top to the bottom step here. So if you calculate the strength or the weight of all these steps, you will realize that is much higher than the strength of the lower step. So this means that the lower step would fracture. In reality, this is not happening. So you have no fracture. So there is another mechanism, another equilibrium state that is happening in these helical staircases that is extremely important, to understand and realize. So this is what we are currently investigating, as well as we are looking at the dynamic behavior of ancient columns and colonnades and how they have used the different drums. Here is a multi-drum column subjected to earthquake, and the different drums act as a dissipating device. And we have many of these columns, even fringe-studding columns, that have survived today because of this dissipating device that is due to the different drums that the ancient Greeks and Romans have constructed. So what we learned so far is that we have frictional sliding resistance or shear strength, we can call it that can contribute to the load carrying capacity of a masonry arch bridge. I would like to highlight here, the important point is that this resistance can disappear suddenly when the formation reaches a tipping point. So you can see a sudden collapse here when it is at the ends. So there is no warning system. And this is the important thing here, that masonry can collapse suddenly. So it's important to understand when this point will reach. Also, masonry structures are gravity structures. They resist applied load through their inherent self-weight. So let's assume like these 5 bricks here. So you need much higher load to push if you have the same bricks, same breadth, but hollow. And if you had half of them, again, lower load. So the strength and stiffness of masonry is affected by material properties, as I mentioned before, very crucial. The method of construction, as I have shown, and existing defects that are occurring in masonry structures. So what I have shown so far is some numerical models that we did and efforts to identify material parameters. So material parameter identification is a crucial issue. I will highlight this again. And so far, engineers are obtaining an idealized geometry, but obtaining the accurate geometry of our structure is extremely important for masonry structures because of what I said before. So based on that, it's extremely important to obtain not only the correct material properties, but also the geometry. So for my PhD, I realized how material properties are influencing. What I'm doing now, where I'm moving, is trying to capture the geometry of these structures, yes. And thankfully, we have some, state-of-the-art equipment that we can borrow from surveying, like terrestrial laser scanners or photogrammetry that can help us develop 3D objects, yes. And even in a millimeter level, we can obtain accuracy and try to capture real-world conditions. I think I'm okay with time, yeah? So based on that idea, I would like to bring this example here. This is a bridge in Lambton. This is in Durham, close to Durham, is in a small city, Chesterle Street is called. It was built by an Italian, of course, Ignatius Bonomi, 1800. It spans like 25 meters from one to the other. It's single span, as you see. Not sure if you are familiar with Durham. Durham is one of the mining areas, used to be one of the heavy mining areas in UK. Because of mining, there is some subsidence potentially. So there is a void underneath due to mining, and this created some movements of the supports. I will explain this to you. So this is how the bridge looked in 1890s. And this is like an image of 1960s. So you can see some damages here at the crown, but also, before you can see like the parapet here is quite flat. So what you see here, it is angled, yes? So it has moved somehow. You can see some damages here. You can see some damages also at quarter span. There is an inverse kick here occurring. And this is how the bridge looks today. In fact, using photogrammetry, we were able to develop a model like that. Yes, so with the technology that we have today, we are able to develop 3D objects of the bridge. So you can see here a representation of my bridge. So you can see here the tilting of the parapet. You can see some damages occurring. I can zoom in. I can look what's happening below. I can see some damages occurring here. It is extremely, interesting tool. And this is all by stitching photos one next to the other. Yes, it's like thousands of photos, stitching them next to the other. So, of course, I can only see the fabric of my bridge outside. I cannot see inside, but it's quite interesting. Yes, it is amazing to see, especially for structural inspection. It's very good. But so far, we don't know how to do with that, apart from looking at it. Yes, some people, they can take some measurements of it, which is great. But I was thinking, can we do something more with that? It is an interesting, 3D model of the bridge. You can see here the hinge formation. So you can see that what happened is the crown have lifted up here. So in a way, the supports are moving inside and the crown is moving up. That's why you see here crashing of the keystone, as we call it, the middle stone here. And then there is a hinge also formation here, which this hinge, so you can see that the crack here is more or less vertical, while here is the hinge is skewed. Anyhow, so I was thinking, let's do something more about this, and they are very good for visualization, as I say, and maybe for understanding the geometry. By obtaining this model, we were able to understand, how originally the bridge has been constructed. In this case, we realized that it was a three-centered bridge, three-center segmental. You can see the three circles. This is the method of construction of the bridge. And you can see how the old bridge, the location here of the geometry of the old bridge and how it has moved now. So it has lifted up by 50 millimeters. So the supports have moved inside, so lifted up. Of course, if you are taking a series of these images and records every 6 months, every year, you can perform some monitoring of this. And to help engineers, but also the people, we have developed an open source. This is like a web platform that someone can just upload photos and develop 3D images. So anyone, the web page for this one is this one, SOC at NCL. This is while I was at newcastle.ac.uk. SOC means Save Our Cultural Heritage. So anywhere you are in the world, you can just upload some images into this platform. The platform automatically merges them, creates a 3D model, and you end up with something like that. So this is like a view of the castle of Kafili. So it's very good for visualization, documentation sometimes. I have used that for some restoration works that I did in Nepal after the earthquake of 2015. So we did some reconstruction. So as I said before, it's nice tools to look at them. Maybe you can take some measures, but I wanted to obtain something more. And based on this passion, together with Professor Milani, as well as with some colleagues from University of Perugia, we wanted to do something more. So we have investigated this Kafili Tower. This is a 13th century tower. It's 17 meters tall. It is 9 meters in diameter. Here, this is the southwest leaning tower, to be honest. It is leaning like that. There are different rumors why the tower is leaning. One of them is that there was a bomb, which we don't believe it. The other one is because of dewatering of the ponds next to it some time ago that created to a settlement of the soil and leaning of the tower. So for comparison purposes, the Pisa Tower is 55 meters and leans 5.5 degrees. This tower is only 17 meters, but leans 10 degrees, yes? So it was important and challenge for us to try to understand what is the maximum inclination angle before the tower can collapse. And what I want to highlight here is that this structure is highly irregular, yes? So it's very difficult, you need an accurate geometry of this structure in order to predict its inclination angle. So we have developed this cloud-to-FEM technology in which someone can grow from a point cloud like that. So we did a survey using a laser scanner, a terrestrial laser scanner, and from a point cloud, we have developed a watertight mesh, a thin mesh, and then watertight mesh, and developed this numerical model in Abacus. We also looked at not the tilting angle also, but the orientation in which angle is going to fall. So you can see here another simulation from the top. And then I wanted to move even further on that. So what we have simulated so far is the tower as a single body. So we can more or less phenomenologically identify where cracks are occurring, but I wanted to identify where the initiation and propagation of crack will occur. So we have used DEM, the discrete element method, to develop such, to obtain such information. So the method is, in very simple terms, what we did is we have scanned the tower, we obtained the 3D point cloud, we obtained the borders of the tower, and then we clean all the points that are inside the tower, and using MATLAB, we have developed an array of the different points in equal dimension from the tower and created this voxel grid system. And based on that, so this tower now is composed of single blocks connected together. What we realized from that, I have some, this work is published, so if someone wants further information can look. But the key point here that I want to highlight is that, the voxels that we created like 25 centimeter voxels, 50, 75, if I remember correctly. But I want to highlight that the size of the voxel as well as the material properties of how the voxels are connected are crucial and important. So the calibration was extremely difficult task for us, yes? So it is like a drawback of the technique. And of course, we can do that, and we can develop further models, so this is the Lambton Bridge that I have shown before. But again, I don't like that much because it has some limitations. You have these voxels connected together and you don't know, you don't have the exact geometry of your structure and where each block is occurring. So I wanted to do a step further, yes, and try to somehow understand how, I can obtain the accurate representation of different bricks in my structure. Yes, so this is my structure. Can I obtain where each brick is located in my structure? So far, what engineers are doing, they are obtaining I call it micro geometry. So the dimensions of the span, how high it is that. But I'm very interested in the micro geometry. Yes, what are the size of each individual masonry unit and how they are connected together. And by having this arrangement, then I can make more informed predictions and more accurate predictions. And this is what I did. So we have used artificial intelligence in this case and deep learning. So we borrow algorithms from face recognition, and we have trained some algorithms. We have used in this case 107 images of different constructions. We have been on the site. We took images. Some of them are from the field. We took the images with mobile cameras, with DSLRs from different angles, just random pictures that anyone, not trained, not engineers can take pictures. And we slice them in 224 by 224 pixels. And we have developed 2,814 images. So we trained the algorithm and we said where the different masonry units are in these. And 25% of these images, we left them for our validation. So we trained the algorithm with most of the pictures, and then we said the algorithm, can you predict this 25% of the images, whether you are getting good results or not? And we managed to get very good results, 96% of accuracy. So you can see here the original image, the ground truth, and the output from the CNN, the convolutional neural network that we have created. So you can see here the end, yes? So someone is able now to identify where its masonry unit is located. But more importantly, also, if you have some gaps like frames here, the algorithm was, or like lintels, the algorithm was able to capture that as well. So this is an upcoming publication. Hopefully soon it will be out in Automation in Construction. So apart from masonry units, as I said to you before, geometry was the key for me in this stage of my career to obtain. Also, what is important to obtain was existing damages in the structures. Yes, so cracks in the structures. So it is important for my numerical model not only to have the exact geometry, but also the cracks. So again, we develop now a separate model. Again, similarly, we train it. 469 images this time. We have done some marking at 351, and we used like 118 images. Oh, actually, 351 images had cracks, 118 images didn't have cracks. And again, we use this 25% for validation, and you can see the result that we have obtained here. So apart from that, so one now can identify where the crack is occurring. But apart from that, you can identify the area of the crack, the length of the crack, and the average width. So you are not only identifying and registering, but you can locate exactly and obtain more accurate information about the geometry of the cracks. Of course, scaling is important. So what we have done is we have like a dial-up. So all this is like in a platform that we build with Python. So someone can, we have used like scaled images. So you have to give like the dimension, let's say, of one brick. And then the code is able to realize and do the scaling. And the scaling can be done also. So so what we did then is we have used the marked image to detect both blocks and cracks. So we have merged them together. Using watershed segmentation, we have been able to isolate detected features and use the polylines here, simplified polylines to define the masonry units and the cracks, as well as you can do also some meshing if you want to do some numerical modeling of it. And something that was very important, especially from the engineers, from the feedback we obtained from the engineers, was can you transfer that into AutoCAD? So you are able also to automatically transfer that into AutoCAD. So from that, someone can more realistically now develop numerical models. This is like a numerical model using a UDEC, a DEM. This is the idealized geometry. So we draw the geometry by hand. And then this is what we generated from the algorithm that we have created. And you can see the low displacement graph that is matching. So this is like the GUI that we have created for this software. And this is like the framework. So you take an image. From the image, you can obtain the location of the masonry units, the cracks. You can develop you can do documentation in AutoCAD, and from AutoCAD you can move into the numerical model. I will finish off with another 2-3 slides. I've spoken for a long time. So this is the two projects that I'm running at the moment at the University of Leeds. This is a 1.8 million project on exploiting the resilience of masonry arch bridges. So what we are currently doing, we're working with the University of Sheffield and Imperial College London, and we are going to construct 3 bridges, 2 regular, 1 skew in the lab. You can see here the progress of the construction so far. And we're gonna test them under cyclic load. So we're gonna replicate a train passing by. We're gonna simulate like 1,000 trains passing by and understand the fatigue phenomena. And we are also doing some small scale tests for characterization, material characterization. And the other project that I'm working is a Marie Curie Fellowship project that we got last year. So what we are working on this is we are trying to develop an innovative live mortar with conductive nanoparticles. So you have nanofillers including in it. So different nanofillers, graphene or carbon microfibers here. You can see a carbon microfiber here in the magnification. So what we are trying to do is you are using like piezo resistivity, and we are trying to obtain the deformation and damage of this structure. So we are developing in a way, let's call it like a smart mortar for repointing, where someone can go outside and using an instrument understand how much has been degraded, has been damaged. So, sorry for that. So what is the future? So the future is the digital, so how we can connect the physical or with physical and like we're using like the digital validation, verification. So the idea is to send that can use the sensors to take some information from our structure, build a mathematical model in the same way as a structure. Also, analysis by using their important only use of that prediction. So if you do that, then you have a better understanding of the behavior of your structures, time, some inspection, cost for repair, maintenance, and avoid potentially a collapse. So engineers like to understand, the stresses that they are accident that are safe. Uh, so the digital twin peripheral issues before they occurring. It's extremely important. And this is my last slide. So this is how I see the future, how I see that we are moving forward. Is the talk of the town. Is not my slide. I borrowed this slide from The Economist a few years back. So it's like towards an integrated approach, as I call it. Yeah, so you have the smart city where the infrastructures speak to each other. Let's say, for example, someone is doing an excavation, is doing a tunnel. Then the information of that can be passed definitely to the bridge above, as well as to buildings next to it. The vibrations due to boring of the tunnel, for example, can activate some dampers in our building or some systems in our bridge to reduce potentially the traffic of the bridge. Or if you have a crack in a tunnel, then some boring equipment, some equipment robots can go and seal the cracks and perform some alterations instead of humans. So an integrated approach is definitely important. It's not the task of a single engineer. Requires teamwork, multidisciplinary work, and this is why we are all here to make the future, to make our society a better world. Yeah. I would like to acknowledge this work is not mine, what I have shown so far. I would like to acknowledge all my collaborators here. Professor Milani is one of them, as well as my funders for supporting my work all these years. And with that, I would like to close and thank you very much for the attention. I hope you're not tired from me speaking for an hour or so.
Vasilis, absolutely not. And, thank you very much. Thank you very much for this interesting speech that highlighted the many keys that are the basis of this workshop. The multidisciplinarity, the needs for the cooperation, and also many aspects concerning the measurement. So I give you the speech to the public in order to say, have you any questions for Vasilis? Please.
Okay. Brilakis. Yeah. Absolutely. I think this is extremely interesting. Thank you very much, actually, for the question and for raising this point. So what I have shown so far is not a digital twin. It's more, some people call it geometric digital twin. So I'm capturing just the geometry at the moment. So all these CNNs and the work that we did depends on data. So the more data you have, the more accurate your predictions. So this is the limitation that we are facing so far, how we can obtain more data. So going to your question, if we somehow obtain data from different structures, how the damage can propagate, then we will be able to make some, we can train the algorithms to understand how the crack will propagate in the future. So I realized that obtaining such crack propagation from real structures is not an easy task. It requires like thousands of, thousand millions of experiments. So what we are working at the moment is developing some numerical models that have been validated from experiments, and then we are using these numerical models to understand how crack is occurring, and using that information, train the algorithms and develop some CNN models based on that for the algorithms to predict us where the crack will occur next, in the next phase. Yes, so you apply, so you have a set of data in which, so you have a structure, you apply the load, and you have some crack, then you apply further load, you see a propagation of the crack, further load, propagation of the crack. So all that information, if you obtain them and train the algorithm to understand, how the crack is propagating, then you can take another structure in the future and then apply the load and see where the crack is occurring. So again, maybe I confused you more, but at the end of the day, it's a very good question, but what is important is data, and we are missing the data at the moment. And exactly. And what we are focusing at the moment is identify cracks that are important. So you have a wall or a structure that has many cracks. The thing is that the governments, the councils, they don't have money to repair every single crack. So identifying which crack is the most important is vital from the economic point of view and from the time point of view to go and do the repair. So it's challenging, but hopefully it's the way forward, and that's why we're here. Thank you.
Other questions, please?
Yeah. In simple terms, thank you for the question. In simple terms, I don't. I can only tell you what's happening at the fabric outside. I cannot tell you what's happening inside. We have put some efforts to use a GPR, ground penetrating radar, for masonry arch bridges to detect whether there are some voids in the masonry arch bridges, not very successfully. More or less, we know where a void can occur, but again, we cannot tell you for certain. So we are going back to traditional methods where you are doing coring and see what's happening inside. Yesterday, we've seen an example of thermography. So maybe this could help us in the future. But I cannot answer this question because we are assuming, to be honest. Especially, you're right, when you have like a multi-leaf wall, you don't know what's happening inside. When you have like a masonry arch bridge, you have the backfill. You don't know how well it's compacted, if there are any voids, no voids. So yeah, it's a limitation of the method.
Thank you very much. Marco, please.
Thank you. Again, a very good question. The answer is no. We haven't looked at that, but these models are definitely very suitable to do something like that. Again, it requires some collaboration with people from electronical engineering to develop the architecture of the sensors, mechanical engineering. But yeah, we haven't done that. So far, my vision was to calibrate material properties or develop strategies to obtain material properties from these structures, as well as to obtain the actual geometry of these structures. But it's a good point, and we can consider it in the future. Thank you very much.
Other questions? And
thank you, Francesco.
I have to like this word, data measurements, and to say that these are the key.
Absolutely.
And what about the uncertainty? For sure, the development of this study, of your studies, can bring us, like measurement guys, develop new sensors, and develop new measurement systems, maybe that can perform online measurements. So have an online monitoring. In your opinion, could be strategic to predict, to include the uncertainty that's tied with measurements? This model.
Absolutely, yes. Uncertainty is definitely everywhere, to be honest. So yeah, stochastic models are extremely important, and we have put some focus into that also, but not the one that it deserves. To develop some stochasticity in that, for example, for modeling especially, not for sensors. What we did is, what engineers actually doing at the moment is, when you have like a masonry structure, you have the bricks and the mortar. What they are doing is they are assuming the same properties for the mortar in the entire structure. However, this is not the case. Even the horizontal joint with the vertical joint will have different properties. You know, during the placement during construction, for example, when the mason lays the vertical joints, due to gravity, the water goes down rather than in the horizontal where it stays. So this creates some different properties. So we have used some stochasticity in that, and some reliability models to understand, you know, a variation of simulations. I think I have some. No, I deleted them. I wanted to put something on that, but I didn't. But yeah, definitely, variability is extremely important, and uncertainty is key.
Thank you so much. Thank you.
Yeah. Well, yeah, Bayesian methods and Monte Carlo.
Evolution of.
Yeah, we have done something similar also. But something, maybe the last sentence that I would like to highlight, that these are all nice technologies, new technologies. It doesn't mean that I'm removing the engineer out of the game. Yes, so the engineer should be there and verify, validate the data, and ensure that whatever the algorithm is giving you is not the right thing. So the engineer should be the one to decide whether it makes sense and I can move forward. So we can develop these nice models, but we still need humans, to take decisions and implement for them.
Thank you so much.
Thank you.
If
Thank you,
there are
everyone.
no other questions, thank you. Now enjoy the coffee break. Thank you.
this first session, one of the parallel session, which is a special session. Actually, the session name is Multi-Domain Measurement for Personalized Comfort Management in Buildings. And this session is organized within the Italian project, the PRIM project, next.com, which is a project about the generation of multi-physics and multi-domain environmental comfort models, theory, elaboration, and validation experiment. Actually, within this project, we are trying to understand how to create new experimental procedures for the creation of new comfort models that can be used based on multi-physics, multi-domain, multi-sensorial approaches to define new way to create models, comfort models that can be used to improve the energy efficiency in buildings. The project is done by 4 Italian universities. So we have Polytechnic of Turin, we have the Campus University, University of Perugia, University of Naples. So let's start this session. We will have 5 contributions, so 5 presentations during this session. And ask to the speaker to stay. We will have about 15, 20 minutes, included the questions and answers. So this is the time for each presentation. So I will start with the first contribution, which is coming from the Campus University with the joint collaboration of Università Politecnica delle Marche. And the title is Combined Use of Wearable Devices and Machine Learning for Measurement of Thermal Sensation in Indoor Environment. Why this? As you can understand, this is part of the work of the project, of the PRIM project. And the fundamental idea is that the living environment is really important, fundamental to enhance the well-being. And the health and productivity of people is highly influenced by the well-being. So what we can say is that the well-being is something that is also physiological, psychological, and so on. Is not only the environment, but is let's say, the relationship that is between the environment and the state of a person in a building. So one of the main, let's say, parameters influencing well-being is thermal comfort. And the idea is that we want to achieve the final goal to heat and cool the people and not the building. So to achieve this, there is the need to develop new personal comfort models to go in the direction of human-centric environmental control system to optimize the energy. How we can achieve this goal? To achieve this goal, we need, first of all, to understand how we can measure well-being that is a such complex quantity to be measured. What are the sensors that we can use to avoid the problems with not to be invasive for the people itself, and how we can use this information to contribute to the development of sustainable living environment. So starting from this point, if we look at thermal comfort, is a lot of years that thermal comfort is used, is conceived in the actual standards using some indicators. The most used one is the PMV, predicted mean vote, which is actually based on a thermal balance and which provide an indication of what is the average response of a large sample of individuals that is exposed to the same environment. However, we have to say that thermal comfort involves really a lot of mechanisms from the physiological point of view. So during the recent years, we are looking at the new research, which is moving from these standards, moving from this concept of comfort modeling toward this personalized, which is based also on the physiological side of the problem. And if we look at this schema, we can see that how we can do that. Thermal comfort is basically the result, and the thermal sensation of occupancy is the results of different mechanisms due to the brain, to the heart, and also to the skin, which is the main interface with which we exchange the heat with the environment. So if we are able, the concept behind the physiological approach is that if we are able to detect, using physiological measurement, to detect indicators coming from these subsystems, we are able to depict what is the actual status of the user. We can use this information coming from wearable sensors to control in a more efficient way the HVAC system, or also to use that for improving also the building energy modeling using this type of information. So The main objective of this work was to develop a methodology, experimental methodology, to measure thermal sensation and to create prediction model just starting from physiological. So the idea was to exclude from the prediction model, to exclude the environment, in the sense that the environment will impact on the person, and then we will measure physiological inputs from people, from the occupant. And using this information, we want to understand, we can understand and predict what is the thermal sensation. Then we can use this information. How we did it? First of all, we built together, here is the next room, which is the controlled environment that has been built in the University of Perugia, which is a highly controlled laboratory where we can change, modify the environment, both from the air side, water side, so we can change air temperature, mean radiant temperature, lighting, acoustics, and so on. So we can really create and replicate different type of conditions. We installed a very large monitoring infrastructure so that we can have track of all the environmental parameters during the operation of the room. And then we integrated also the physiological sensing side. All the data are collected together. So we have a large database of data that are processed, cleaned, and then they are processed to create some what we call clean user data. So with this infrastructure, we are able to create this large data set where we can then apply data analysis or further analysis also after the project that can be used to improve the knowledge about comfort, about well-being, about the interaction between people and the environment. This is the experimental procedure that we applied in the first part of the project. This is one of the largest campaigns of this type. Actually, we enrolled 50 healthy subjects that were asked to participate to 3 tests under different thermal conditions. The idea is that in each test, we want to stimulate a different thermal sensation. So cold, neutral, and hot. And the protocol that we used is that one. So before the test, there was an explanation and collection of general information about the person that is going to do the test. Then 15 minutes of acclimatization, so that if we want to measure the cold sensation, we need to have the cold sensation, okay? And then after this acclimatization, also, this is a rough measure, this 15 minutes. In some cases, we asked to the people that were inside, to subject that was inside, if there was in reality this kind of sensation. And then we started the recording of physiological parameters, as we can see in this picture. So we just used these 2 sensors that I'm going to explain in the next slide. At the end of the test, so in total about 20 minutes, 30 minutes, there was the collection of the subjects were asked to compile a survey so that we can collect the information. The survey was very large. Now I just present one of the information that we collected that is used for this scope, which is thermal sensation, that was collected with a 5-point scale, 0 neutral, negative values for cold sensation, positive value for warm sensations. And this information has been used, so the thermal sensation vote was used to label the data that then in the second phase we used for the machine learning purposes. Concerning the measurement, we tried to select the less possible intrusive solution. Sorry, I just removed the mask, I forgot. Better. Concerning the physiological measurement, the idea was to select some sensors that are really not invasive, so that we don't create a disturb in the measurement that we have done. We used the empathic IFOL, which is a medical grade device that includes several sensors measuring basically PPG to measure their heart activity, so the blood pressure volume and the interbeat interval. The electrodermal activity, EDA, for the galvanic response of the skin, and a temperature sensor for the skin temperature measured so on the wrist. Concerning the brain activity, we used a commercial solution, which is the Interaction Muse. This is just a meditation. This is used for doing yoga, but it's really no intrusive. We have low resolution because we have this sensor has just 4 electrodes to measure the brain activity in the front-hand side and in the temporal side according to the 1020 international system. And this used wet electrodes. So really, in 1 minute, the sensor can be weared, can be used. So we have really reduced the time of setup of this kind of measurement. Then, obviously, if you use wearable, low-cost, non-invasive sensor, you need to do some signal processing because you will have some noise. You will have to clean the signal. So concerning the EEG, we made noise filters. So we used bandpass just to get the information in the frequency ranges where the physiological brain activity is actually present. And we removed, with the independent component analysis, we removed also some facial artifact like the eye blink. And we calculated the power bands. Power bands allows us to calculate what the so-called brain waves. So the amount of power in a certain range, in a certain frequency range, that are correlated to a certain state of mind. So if you are focused, you are concentrated, you are sleepy, and so on. Concerning the other signal, we removed the ectopic beats from the interbeat interval measured with the empatica. We removed the artifact on the EDA signal, and we calculated the tonic and phasic component of the galvanic skin response. So tonic and phasic basically are what we can say the AC and DC component of the signal, which are related to different mechanism in the thermoregulation of the body. All the data were synchronized, and we extracted a set of features. Features are our indicators to detect the physiological state of a person. Concerning the EEG, as I was saying, we just used powers because with this kind of low-resolution sensor, we cannot do some analysis like pattern activation of the brain or something like that. You can just understand what is the state of mind of a person. Concerning the interbeat interval, we calculated both time and frequency domain analysis, tonic and phasic component for the EDA, and temperature of the skin. In total, we had more than 100 features available for the analysis. To understand what are the features correlated with the thermal sensation, what we did is to make some statistical analysis. So we applied the repeated ANOVA for Gaussian features, distributed features, non-parametric Kruskal-Wallis for non-Gaussian one. And finally, we also did a pairwise comparison, so a post-hoc analysis to understand what is the capability of each feature to discriminate between, for example, cold and warm sensation, cold and neutral, and so on. This is an example of the data that we acquired. So here we extracted one of the data measured from one subject that was exposed to 3 different thermal sensations. So we have both the cold, the neutral, and warm. And so what we have seen is that, for example, looking here at the EEG results in the power spectrum of the EEG, we see that with the thermal sensation, there is a real change of state of mind that can be detected. So, for example, there was a higher activation. When you are in cold sensation, you have higher activation of the temporal side on the right side of the head. Or if you are warm, you are in the opposite, you are more alpha power always in the temporal side. Also concerning the heart rate variability, we have seen that increasing from cold to warm sensation, there was an increase of the power. So an increase also in the ratio between the power in the low frequency and the high frequency. So the so-called LF HF ratio. And the same we have seen also, as we can see down, for temperature and electrodermal activity. So for temperature, we saw a higher temperature of the skin and also a higher tonic component, because there is a different, if you are in a warm condition, you have more water on the skin to improve the heat exchange. So you can measure this with this change in galvanic response of the skin. Now, this is a very nice to see, but it's not always like that, because when we look at the whole data set, there are a lot of inter-individual differences. So it is not always easy to find this situation in any case or in any subject. So that's why we did this kind of large campaign to understand in the average what happened and to understand what are the really most significant features that really can be used to understand the thermal sensation. And this is the results from the statistical analysis. I'm sorry, it's a little bit small picture, but actually we found out that we have about 25 features that we can use because they are really presenting statistical significant differences in the different thermal sensation, in the different thermal conditions. So as we can see also here from the 3D map, we are able to detect some zones where we can say if there is more probability to have a cold sensation or a warm sensation. So starting from this statistical analysis, from these first results that we achieved at the end of the experimental campaign, we start to be sure that using this data, we can train some prediction models. So we can really create a personal comfort model. And this is what we did using the machine learning techniques. So we divided all the data set into training, 70% of the data, and the validation test. We used the CUDA toolkit to have enough computational power. And we also applied some optimization, basic optimization based on Bayesian approach of the hyperparameters. The first classification we did is binary. So let's say with this model, we want to have something that starting from these features, physiological features, we want to just say if a person is feeling hot or cold. And given the heuristic approach, these kind of models, we made different iterations. So every combination, we did different combination of physiological signals. We iterate several times because in this way we have more accurate analysis of the results. Because if you run different times the same model, you will have always you train different times the same model, you have always a different result. So you need to do that several times. In this first step, we just tested the 4 classifiers, which are the KNN, linear regression, Gaussian naive Bayes, and random forest, which are the most common used, also starting from the state of the art, so the literature that we analyzed. This is the result that we achieved. Actually, in general, now here I'm showing just the accuracy, but we also analyzed others that are presented in the paper that you will find in the proceedings. Because of time, I have to close this part. Actually, in the average, the accuracy was between 0.55 and 0.86, so very good accuracy. And here, as we can see in this plot, we show the results coming from the different classifiers that we used, also with different combination of physiological signals. Because the idea was maybe it is not always possible to have all these sensors applied. You know, if you think about real life, how we can apply this in real life. So we made some combinations using different signals together, but also comparing with all the signals together. Obviously, the most performing results was achieved using all the physiological signal. But I have to say that also using, for example, skin temperature and EEG was a good combination. So we reduced a lot the number of sensors to be applied, and we achieved a good prediction accuracy. One consideration is that the poorest results were achieved with the PPG. We thought a lot about this, and actually we identified 2 main problems on that. The first one is that the signal processing that is on board on the Empatica, on the device we used, is not that good, because if you have artifact movement, it just cuts the signal. So it removes a lot of information. So this is one of the main problems. So there is the need to improve this part of the signal processing. The second one is that among all these parameters that we have, all these physiological signal, the PPG is the one, so all the features related to the heart rate variability is the one with the more important impact of the inter-individual influence. So there is probably the need to do a kind of calibration to measure what is the heart rate at resting condition, use that as baseline and make a normalization of the data. So that's why this is how we justify this poor result using the PPG, that actually is one of the most used in literature for this kind of personal comfort model development. So going to the conclusion and the discussion about what we achieved. So from this experience, we can say that the multimodal signal analysis is possible, and the channels, the physiological signals that we identified are really good for this scope, because we found that we have statistically significant features that can be used to train the model, and the models that we trained achieved a good accuracy. So this is the good news. among the different classifiers, we found that the Gaussian naive bias is the one that, maybe because it's based on this Gaussian distribution, which is really one of the typical distribution of physiological signals, is the best one. And so this is what we achieved, and for sure this paved the way for the next step is to improve this kind of model. So we can exploit this result to better investigate indoor environment and to use this to control the indoor environment starting from comfort sensation. This study probably can put also some, let's say, pillars in the development and how to develop a personal comfort model that can be used in the future in the real context, so for real life application. And another important conclusion is that we were able to measure thermal sensation without using the environmental data. And this is really important because sometimes thermal sensation is not only related to the environment, but is also related to the personal state. So using this kind of approach, we can enrich the information that we can have, which is, now, let's say that now we are using the environment, we are controlling just measuring temperature in one point in the room. So using this kind of approach, we are really enriching a lot the information that we can use to control the environment. So this can really pave the way for the future of this sector. Future direction, so for sure it's to improve the machine learning, so to continue. We have a lot of data. Actually, also in this period, we are doing other tests, so we are collecting other data, so to enlarge as much as possible this data set. So we are going to enlarge the sample size. We want to test also different classifiers to improve also the way we use these classifiers. So, for example, the selection of the threshold to be used for the classification and so on. We will for sure enhance the PPG measurement. We want to investigate better how we can use this measurement, because PPG is actually very much used in smart watches, smart bracelet, and so on. And finally, also within this project, we want to integrate this prediction model with some buildings energy simulation models. And this is really important because we want to understand what is the impact, because for sure we can improve comfort for people in the building using this approach, but we have to understand what will be the impact also from the energy point of view. So we will be able also to improve the energy efficiency. Let's see it. We have to understand, to investigate this point. So thank you so much. I would also to thank my collaborators, so Gloria Cosoli, Silvia Angela Manzi, that worked on this part of the project, and that's it. Thank you so much. If there are any questions, please. Yes, please. Yes. This is a very good question. The reason why we use it always EEG is that starting from the literature analysis, we have seen that there are a lot of works that are using PPG, galvanic response to skin temperature. Very few about EEG. So when we performed this training, we always kept the EEG because we want to improve the knowledge about that. But for sure, what we will do is also, actually we started, also train models using other combinations. So using, for example, only skin temperature with the electrodermal activity, or PPG with the skin, and so on. Yeah. Yeah. This is a very large part of the work we did at the beginning. Actually, we in this moment, we had 50 subjects that did, at least each one did the free test in the free conditions, but also in 2 different seasons. Somebody in summers, others in winter. So at the moment, we have about 250 test data set of tests. And we did a lot of synchronization. So we had to take all the timestamp because you have also different sampling frequency. So some signals are 64 hertz, other are 256, and so on. So what we did is that to synchronize the timestamp and then to calculate the average per minute. So for each minute, we have the average of the features that we calculate. So, okay, if there are, please, Forrest. Yes, this study is based just on these three. No, exactly. So we used the environmental data to understand what is the situation. We excluded the data, so are just control variable, but we are not using for the prediction. What we are doing now is also to change in a different way. This is the first study, but now we want also to change, for example, creating some discrepancy between radiant and higher, or changing also, for example, the color of the light and so on to understand what is the impact. But this is the first study, and we want to demonstrate the feasibility of the wall approach. Now we are changing the experiment. Perfect, perfect. Thank you so much again. So we can move to the next work, which is presented remotely, actually. Enrico, can you hear us?
Yes, sure.
Okay.
Can you see my screen?
Yes, we can see. Just presentation. The next work is presented by Enrico Fabrizio, and the title is Application of Multi-Field Sensor into an Office Building. So if you can mute your microphone, Enrico, and then you can start. But you should also share the screen.
I mean, you can see the screen or not?
Okay, let's try full screen.
Yeah, just I would like to.
Okay, we can see.
Oh. Yeah, sure. I just have to reduce the volume. Okay. So perfect. Thanks, Professor Arnesano, for organizing this session and also for inviting to join you in this session. So I'm going to present a work which was developed in close cooperation with a company, which is the Delta Control company from Italy. It is about the application of a multi-field sensor into an office buildings. We all know that there is an increasing interest in building automation and control systems. For example, in Italy, as of 1st January 2025, all new buildings, commercial buildings, will have to be supported by BACs. And there is a large use of BACs, a large amount of sensor that monitors even smaller portion of buildings that are increasingly used. And we should be able to use those potential of BACs not just to reduce the energy consumption of buildings, but also to control the comfort, the thermal and visual comfort and behavior. So the objective of this work is to present you the implementation into 4 office buildings of the testing of a new multi-field sensor, which is marketed by this company, considering the operation, the placement, calibration, and the analysis of monitoring data. So this O3 hub sensor acts in the system, replacing multiple room sensor with a unique component. It is installed with a sort of controller, which is this one. What is peculiar with respect to other multi-field sensor, it's the interaction with the user. So the occupants can also select from list of settings through a mobile app how to manage the thermal comfort and indoor quality if there is monitoring for the CO2. So the O3 hub in the room, in the enclosure, directly communicates with a controller that contains the memory storage, the external communication ports, and also some expansion modules. So the system runs through a BACnet protocol, in order to control all the aspects of the room, that is HVAC system, but also lighting, the blinds, the access, the presence of the people, etc. The main difference between a space which is monitored by an O3 hub and other families of controllers, such thermostat on the wall, sensor, locks, meters, etc., is that this single object can absorb all the information from the sensor, and in the controller, it can elaborate some algorithm based on the quantities that are measured. So something about the sensor fusion, the 6 quantities. For the air temperature, actually, there are 2 inputs, 2 analog inputs. There are 2 measures, and one is a composite value of an algorithm that keeps the information on the estimated temperature and on the variance of the temperature. The algorithm uses an approximation, a quadratic approximation, to model the temperature readings all of the time, and it takes into account also to some statistical noise to reduce the noise on temperature readings to make temperatures more accurate as possible. If the installation is respected, the output temperature should be quite close to the value that may be read by a thermostat in the same room. Then there are other sensors. The infrared temperature sensor is a thermopile. It covers a surface of around 6 meter of diameter to 5 meter of diameter as a function of the installation height. And generally, the infrared temperature is likely to be slightly lower than the air temperature that is right at the ceiling. There is also a humidity sensor with a measure at the ceiling and an approximation at the level of the people. The light sensor measures the illuminance, the lux at the ceiling, and this is why it is necessary to adjust it, since we want to control, for example, blinds or artificial lighting should be it should be adjusted in order to be representative of the illuminance on the work plane. The motion sensor is a binary input. The occupancy is set to 1 if both the motion and the sound is triggered. There are 2 microphones in order to measure the audio levels also. The experimental setup is such, so we are into a sort of, let's say, office building for different office room. One is meeting room, the other ones are working rooms, etc. Later we call room A, B, C, and D. We installed 4 O3 hub sensor, 2 controllers. There were experimental measurement and data for 6 months, from September 1st to February 28th. The sensors were placed around 3 meters of height in the different rooms. All rooms are heated and cooled by a fan coil, which is controlled by the backnet network. And while the first 2 rooms have also a ventilation system, a primary air ventilation system, room C and D just use natural ventilation through windows openings. So something about the first calibration at installation, so calibration at the site. A procedure to calibrate room temperature and other inputs is provided by the manufacturer. So we did measurements by using 2 normalized sensors placed at occupant's height. The resulting adjustment for temperature are always negative, in the sense that we should reduce a bit. We were in the winter season also, so reducing between 0.7 and 1.7 degrees, and conversely on the relative humidity we should increase. This just depends on the correction on temperature. What is more interesting is the light calibration, because as regards the light level, the O3 hub measures the mean illuminance at the sensor surface. So several lighting simulations were done of the actual rooms by using Dialux software tool, in order to retrieve some correlation with the readings of the hub. So the geometrical model were done, the simulation were performed in clear sky, intermediate sky, and cloudy sky. And these are examples of the linear correlation between the hub calculation surface and the work plane calculation surface. So it can be noted that the clear sky increases the dispersion of the results in comparison of the cloudy sky, which is it's linear. And so in general, the higher the luminance which enters the enclosure, the larger is the difference between the sensor reading and the illuminance on the working plane. Some results on the temperature measurements and some comparison with measurements taken from existing thermostats. So temperatures of room B, in this case, before and after the calibration, are reported in the first two diagrams. And finally, the resulting quantity is compared in the third diagram on the bottom with the measures by a wall-mounted thermostat, which was made a passive sensor, so it was not included in the calibration process. In order to read the graphs, well, full lines means measured variables, dashed line means elaborated variable from the measured one by the internal algorithm of the O3 hub, and the green lines means adjusted variables. So after the adjustment, the room temperature deviates from the ceiling digital sensor values on the top. So since we are around 3 meters of height office, the temperature gradient from the floor to the ceiling, these are day in September, is not negligible. It can be noticed that both graph the difference is around 2 degrees. So first it is under adjustment and then post the adjustment. In order to have an accuracy reference, a comparison between the adjusted room B measure and the measure from a wall-mounted thermostat was done. So here the maximum difference between the two sensors is just 0.2 degrees. So even though one is on the wall and the other is on the ceiling. And which is more interesting, the fact that the continuity, let's say, of the O3 hub measurements can be appreciated in comparison with the measurement from the thermostat. So this is due to the algorithm, and we avoid those instant spikes in readings that should not be taken into consideration when we use those readings to control the HVAC. This is similar, but the spikes are larger because in this day there was an effect from the solar radiation, so that modified the temperature reading by the standard, the wall-mounted thermostat. And at one point, there was also a change into the set point temperature in the office. Now, combining some measurements, some temperature, relative humidity, etc., here an example of what can be done. Combining temperature and relative humidity, these are a sort of dispersion diagram that represent monitored value every 10 minutes of 1 day. The parallelogram is the standard comfort thermal zone for a value of 1 kilo of insulation. So especially at the beginning of the day, it is possible that occupants feel uncomfortable, but the main use of this diagram is that one can soon see whether the HVAC systems are designed correctly, manage to keep the internal parameters within comfort ranges, and on the other hand also if there is room for energy savings, since for example the control of the hours from the unoccupied hours means that at the end of the day we should reduce the heating in order to save energy, because there are many unoccupied events, so every 10 minutes, that fall within the thermal comfort zone, and this will not be necessary. So if we look at the broader scale, so looking, for example, at 1 month, here are some results from the February 21. There is the exceedance hours from both temperature and relative humidity. So temperature that goes above 20.5 degrees and relative humidities which are quite low, lower than 40 or at least lower than 30%, which is quite annoying, quite a discomfort causes. So basically the discomfort generates from the outdoor air temperature variation, which is plotted in against the values which is plotted in black, the black line. This is the chain is that the hot water in the heating loop is controlled by the outdoor temperature, by a climate relation. So the colder the weather, the hotter the water, and the higher the temperature, and finally the lower the relative humidity. But in some cases it means very low values. So around 70% of this value were lower, and the combination of lower temperature and high relative humidity occurs for a very small portion of time. So finally, what can be concluded? These systems are quite useful and interesting. These are commercial systems. I would like to stress the fact that this was a research activity, but we kept it quite simple and easy, because that was the request from the company, for sure. So it is not straightforward to configure and to adjust the sensor hub. So all the calibration process that I summarized, the fact that if one want to use it for controlling the shadings, for controlling the artificial lighting, it should be really calibrated considering the lighting values. The installation height is really important. So sometimes the temperature readings are not reliable. There is the problem of season. So this analysis was basically made in winter, but we are going to keep the analysis also on the summer season, because that will change some parameters. So for sure, these are quite there is an increase in versatility of such type of sensor. They have multiple applications to be discovered, but there is still some research activities and technological activities that should be done in order to be completely useful for the people, and for also be integrated into the standard, into the useful control system of the building, which means the shadings, the lighting, the ventilation system, the fan coils, etc., that today usually are controlled by different closed chain and closed systems. Thank you for your attention. I cannot hear the question. I mean, I just can hear the speaker. Okay.
Yeah. If there are any questions, please, the person is asked to come here to do the question. Is there anyone? Okay, I have one. I have to move.
No, I can hear you, Marco.
It's the same. Okay. Thanks, Enrico, for the nice presentation. I have just one question about the calibration of the temperature sensor. So if I understood, you need to calibrate because you install on the ceiling of the room. And what about the potential influence? You know, if you change the environment, maybe you have different air distribution, vertical distribution, how it can be considered, or is it considered, or you have to think to do a calibration every time you do a new installation?
Well, my opinion my opinion is that yes, you have to do a sort of calibration at each installation. So at the moment it is not possible to consider such sensor like a thermostat, a wall thermostat, etc. But there is the fact that the infrared temperature measurement is more reliable than the air temperature measurement at the ceiling. So especially as regards the airflow into the room, so the final value of room air temperature at the occupancy 8, so 1 meter, 1.5 meters, etc., is made from an algorithm. It can be reported in the manufacturer sheet. You can find it, etc. I mean, but it takes into account also the infrared temperature, which is the one that, I mean, adjusts really the values. So combining the local adjustment plus the adjustment from the algorithm, from the internal algorithm, that is mainly based on the infrared temperature of what can be seen, because basically the objects at 1 meter are around the same temperature, the air temperature at 1 meter, that helps. But if you have all air system, for example, that may be quite challenging. If you have a ventilation system that has an efficiency, I mean a displacement ventilation system, let's just say, it will be quite tough and challenging to calibrate and to obtain accurate temperature estimates.
Thank you. That's what I was thinking about exactly. This kind, if you have this kind of ventilation, of course you need to make some adjustments. So thank you again, Enrico. So
thank you, and sorry for not being here.
Thank you so much.
With you.
Perfect. So we can move with the next work, which is long-term thermal comfort monitoring using wearable devices. The work will be presented by Veronica Martins-Gnecco. Please, the stage is yours.
Should I?
Yeah, you should open.
Okay, hello everyone. I'm Veronica Gnecco. I'm a PhD student at University of Perugia. And I'm going to present the article entitled Long-Term Thermal Comfort Monitoring Using Wearable Devices. So we are going to start with a brief introduction, method, results and discussion, and then the conclusions. So the human comfort in indoors and outdoors environments has been studied by many researchers in different fields in the last years. And predicted mean vote, which was developed by Fenger in the 60s, helps to access the human dimension of comfort, perception, and research. And this scale, it's a 7-point scale, and which goes from -3 to +3, and represents the human perception of comfort. And it can be adapted for different points, like a 5-point scale, as Marco presented, or even to represent non-neutral thermal conditions, thermal preferences. And this subjective sensation of the occupants can also be associated with environmental or physiological data, and we can identify preference patterns of occupants. And wearable sensors are an option to catch this personal human experience of comfort, such as probes, headbands, and smartwatches. And this type of wearable devices are practical solutions and also non-intrusive and available commercially. And considering that, the aim of this study is to investigate the correlation between the mean daily thermal sensation vote and the daily mean normalized temperature during long-term monitoring using a wearable device. So the first step of the method is the data collection characterization. 6 people were asked to wear eye button hygrochron. It's a probe, like a keychain, to resist the temperature and the relative humidity. All of them are women with very similar routines, working in research and similar age. So we have a very homogeneous group, and all of them were in Perugia during the campaign for at least 1 month, wearing this eye button hygrochron in different seasons of the year. And also they were asked to answer a survey 3 times a day, right after waking up and between midday and 2 p.m. and also right before going to sleep, about different comfort dimension perceptions. But in this case, we use just the thermal one. And I have to say that one of the subjects have a low attendance to the survey, so we have to exclude it from the sample. So we keep just 5 people in the sample. And also that the scale that we used to represent the thermal comfort perception was a 5-point scale, as you can see in the table. The second step of the method is the data analysis and clustering process. We use Python routines to normalize the mean daily temperature. So we took the minimal temperature for the day and subtract the mean hourly temperature from this value for each day. And having this normalized mean daily temperature profiles, we perform the K-means cluster method to see the lower to higher variation of our hourly temperatures. And also the number of cluster was determined by the lower mean within cluster average values, and each cluster has to have at least 10 elements. And also we calculated the daily mean TSV for each day. And the last part of the method was the statistical analysis. We perform an experiment test to verify the correlation between the mean daily normalized temperature and the mean daily TSV. And we consider that if you have a p-value higher than 0.5, there's no evidence that there is a statistical correlation between the TSV and the normalized temperatures. And if the p-value is lower than 0.5, we consider the counter hypothesis of the H0. And also the standard deviation of normalized temperature was calculated to see which cluster has the higher or lower variation of temperature. And this procedure was repeated for each subject and also for the whole database together. So the first results, in the table you can see the within cluster average distance, very similar for all the subjects. Only the 5-1 because it has a lower number of answers, so we have a smaller database for in this case, and also a small number of clusters, just 2. So the distance to the centroid it's a little higher, and the number of clusters vary between 2 for this subject 5 and 4 for the subject 4. Here you can see in the graph the distribution for normalized temperature, and in this case I only put the representation for the whole database, and the cluster 0 is the one of the bottom. It's the one with the lower temperature variations, and we can assume 2 hypotheses. The first one, that the person is at home, so in a controlled environment with more freedom to modify and use different artificial strategies to improve comfort and keep the temperature with lower variations, or if the person just forgot the probe at home and didn't register the modifications of temperature during the day. But we also can see that between 9 a.m. and 8 p.m. we have a higher amplitude of temperature, probably because the person is outside, so it has a higher variation without any control. And in the other hours, from 8 p.m. to 9 a.m., the variation is lower, probably because the person is at home and, as I said before, can control more the environment. And also due to the lack of answers concerning the thermal sensation value, so the surveys, we only keep the 17% of the expected answers to the next step. So this might be a problem. So we lose that data because of the low attendance to the surveys. And here we can see the results to the experiment test. And it shows rejection of the H0, so we can assume that it might have a relationship between the two variables in only two cases, so cluster 1 from participant 1 and cluster 0 from participant 4. And maybe we can see that it has a tendency of correlation between the lower temperature variations. However, this test must be replicated with other sample size and also a more heterogeneous sample to see if this results is also the same in other cases. And for future research, we think that we can establish new campaigns with a higher number of samples, also during longer periods of monitoring because we use just 1 month. And also heterogeneous samples, as I said before, so different routines, metabolic rates, age, and everything. And one thing that we saw that was very important is to engage more the participants to the data collection, because this type of research that we are not controlling, like in a test room or maybe in a in-field test, the researchers are not there all the time, so we can't control what the user is doing. So we have to clarify to all the participants the importance to do the things in the right way, like answer the surveys and also wear always the probes. So it's very important to clarify this to the participants and engage in the research. And also for our future research, we're thinking to include other dimensions and variables like the visual and acoustic dimensions, because we asked this in the survey, but we didn't include in this research. And also other data like heart rate data, stress level, and also sleep quality, because we also use the Empatica watches to record data, so we can do other things in future research, including also the physiological data. So that's that. Thanks.
Thank you. Are there any questions? Yes, please.
Yeah, we now are doing another research similar to that, also using smartwatches that can have other types of measurements, also skin temperature. So we are thinking to do the research using the physiological data, also the surveys and the environmental data. So we're trying to get everything in the same research and try to see other types of correlations.
I have just a curiosity about, you use the eye button sensor for the temperature. What would be, in your opinion, the impact? Have you seen in the data collected some strange data if you treated them? Because, you know, this depends how you are wearing the sensor, if you are in contact with something else or there are other sources.
Not strange data, but we see that sometimes the person is not using the data, the probe. So it's a large amount of data, and sometimes it's hard to interpret this data, because it's not so visual like the Empatica. It's more human related, so the eye button is not so human related. So because of that, I think it's important to correlate the physiological data of the smartwatches and also the Empatica, the eye button.
So using the data for the analysis that you presented, you you haven't removed some, let's say, outlier due to this.
Actually, I
remove
didn't
it.
put it, but we removed some outliers.
Okay, so there were.
Yeah,
so there is the need to clean the data.
Yeah, when we did the normalization, before doing the normalization, before that I removed some outliers from the database. Yeah.
Okay. Yeah. Yeah, please.
So if the IBEF gets hit by the sun and it does a 60, is that irrelevant?
What, sorry?
Is that irrelevant to the person's
Yeah, but maybe it's not the thermal sensation of the person, so it's more environmental data. So because of that, I think it's different from the thermal sensation, and we have to relate also with the surveys and also the skin temperature and other type of data. Okay.
Great, thank you. If there are no more questions, I think we can move on. And actually, Forrest give really the good connection with the next work. That is about improving mean radiant temperatures using multi-directional non-contact temperature sensors to avoid convective errors with globe thermometers. So the work is presented by Professor Forrest Mengers, from Princeton University. The floor is yours.
Thank you very, very much. Thank you, Marco, for inviting me and giving me an excuse to come to Calabria, eat delicious, spicy food. I'm very excited to be here to talk about, of course, the good, the bad, and the ugly, because in Italy, we have to talk about spaghetti westerns if we're coming from America. But it is the framework for what I'm going to talk about, hopefully quickly today. As Marco mentioned, I'm professor at Princeton, where I am the self-described professor of chaos. So I, of course, have put in a lot of extra slides, and I may skip over a few for the sake of time. But what I'm going to try and cover today is why is mean radiant temperature an important thing? And then two things, why is it problematic, i.e. bad? And then what is significantly wrong about how we measure mean radiant temperature? But as with all spaghetti westerns, there will be a happy ending, and I will show you a simple experiment that we did with some alternative sensors that we have here today to share with you. So to start with, very briefly, the good. Hopefully most of you are familiar with mean radiant temperature. So this is a variable that we use to describe the average radiant temperature surrounding a person in theory. Technically, the definition actually means that it should be the average temperature of, if I averaged everything around me, it would be the average temperature that would create the same radiant heat flux onto my body, which a lot of people forget that our bodies aren't spheres or aren't these things that we use to measure it, which is one challenge. But it's still an important thing to measure because it is a critical component of thermal comfort, as we've already heard many talks this morning about the different pieces of thermal comfort and how we measure it. The one I'm going to be discussing very extensively is radiation and how thermal radiation affects our thermal comfort. So the classic variables that we would measure are more often temperature, sometimes humidity, and ideally some air movement, but I argue radiation is the one we measured the least. And in spite of measuring it the least, in this room right now, about half of all the watts of heat that your body is experiencing are coming to you in the form of photons, not in the form of convection from the air, though all of these systems in the room are controlled by a sensor measuring only the air temperature. If we're lucky, there's probably a thermostat. Maybe it's that guy over there, that guy over there. Oh, but maybe there's a little globe on that one. I can't tell. It's hard to tell. Yes. But this isn't something that is new. We've known this for a long time, since the 60s. The Olga's architects, actually, from Princeton, tried to include radiant temperature in comfort maps about bioclimatic design. We've been talking about ways that we can model the human body more accurately, and we've discussed already a little bit of that today, thinking about how physiology is very important in our perception of thermal comfort. But I'm going to step back today and away from physiology and argue that we're really getting the physics wrong in the environment a little bit first, and that there are some things we should fix there before, well, not before, but we should do both. We should do physiology, but we should also make sure we're getting the physics right around us in the environment. One way that we've tried to do this is with this tool we call expanded psychrometrics. Eric Teitelbaum and my group developed this a few years ago. We bought these clever URLs where you can go to this online tool, which just does a model of the human body and puts it on a psychrometric chart. So instead of just doing temperature and humidity and putting a comfort zone like we would usually on a psychrometric chart, which I also think is problematic, we plot a map of the potential mean radiant temperature you would need to be comfortable at any point on that chart, because the temperature and humidity are just two variables in a heat balance of my body, which was in this equation here, is just a heat balance of my body. And so if I just compensate for how those are changing by changing the radiant temperature, you can see in theory, I can balance out the heat of your body using any environmental variable, in this case, mean radiant temperature, but we also made a version where I can change the airspeed. In theory, we have those 4 environmental variables that we can change. The challenge, though, is when I go out in the real world and we have the problem with the thermostat, that in fact, it's easy to measure air temperature, but very hard to measure the radiant temperature in spaces. So this brings us to the bad part of doing building comfort when we're thinking about mean radiant temperature and comfort, which is that we're often in spaces that in fact aren't comfortable. In fact, if we think about comfort, there's a lot more value. For every dollar we spend on energy, we're spending $10 on rent and $100 on salary. So having the bad metrics that aren't measured properly or not measuring all the variables is problematic if we really want to affect people the best way we can. But unfortunately, we're tied into something that we invented in America only a century ago or so. It's only been 100 years that we can artificially make this room cold with air conditioning. But even though it was very cool that he invented air conditioning, sadly, we've trapped ourselves in this modality of blowing cold air around. And I would argue that the more important thing that Willis Carrier invented is in fact the psychrometric chart. So he invented this plot that tells us how temperature and humidity are related, which, for context, was never meant for thermal comfort. This was just meant to tell engineers how to control the coil temperature on their air conditioning system. We are the ones that then decided, in order to make these buildings comfortable that are now all air conditioned, and none of these style of architecture could ever be possible with this much glass without inventing air conditioning. And once we built them, though, we decided there would be a spot on the psychrometric chart that is comfort. But again, this is only 2 of the variables, and they happen to be the ones that we can control with conventional air conditioning systems. So I'm arguing that we can go back and rethink this standard modality of psychrometric chart and standard air conditioning and rethink the sort of comfort standardization that we have, because we have all the other variables in our comfort models. As we've already discussed today, they're there. The problem is that we keep focusing back on the psychrometric chart. And I love to point out this one, which is from ASHRAE, where the operative temperature is on where the pointer is, but if the axis there says operative temperature, which just for context makes absolutely no sense, because now the physics of the psychrometric chart are broken, because the operative temperature has nothing to do with how humidity changes in air. So this just goes to show how far, in some ways, comfort has sort of broken the conventional air conditioning control system. And it brings us to a place where we constantly say things like, this room is comfortable based on measuring the air temperature. But I would argue that a room cannot be comfortable. Only I can be comfortable in a room. So back to the person part of this session and thinking about people, I argue that yes, we need the physiology, but first I need to have a better model of how the environmental conditions affect the person in the room. So not using the psychrometric chart, but thinking about how I measure some of these other variables, such as mean radiant temperature. And so what we've done in our group is try and find better ways to measure it. And we've built all kinds of crazy things like this thermal heliodome that reflects radiant heat and allows us to make people feel cold outside. We built the Singapore pavilion where we were able to make people feel like it was about 20 degrees Celsius perceived temperature in a 32 degrees, 80% humidity outdoor environment. So that's my friend Adam Rieseneck there. This is a 33 degrees Celsius, mean radiant temperature of 20. So the felt temperature was more like 24 degrees. But the problem is when we go to evaluate these pavilions, we kept running into the issue that these globes just wouldn't measure what we thought the values were in our models and our simulations and what we were measuring with other pieces of technology. So this brings us to the fun part, the ugly, which is the unfortunate fact that the way we measure mean radiant temperature today in probably 99% of thermal comfort experiments maybe not 99. Thanks to Marco and some colleagues, we are using other devices and there are other ways. But the one that we use most is this guy. So most people have probably seen, if you've ever dealt with measuring indoor environmental conditions, the globe thermometer. It was actually developed in the 30s. And one hilarious piece of history is that the original 6-inch globe is actually a float from a toilet. And that just became the standard piece that we always use. We paint it black. And it used to be used in parallel with a silvered globe. So the way it worked is you'd have the black globe that would get radiantly warm, and then you would heat up a silver globe to the same temperature, and the energy it took to heat up the silver globe would be the convective losses. And so we could correct this black globe for the fact that when it gets warm, it gets cooled down by the air that's colder than the globe. Unfortunately, that piece of correction went away and became a correction factor that got added into the standard methodologies, both in ISO and in ASHRAE. And what we discovered is when we deployed these in all of these experimental pavilions, the globes never gave us the temperature when they were corrected anywhere near what we thought the mean radiant temperature was. And that was because, unfortunately, this old paper that I had to find for Richard Didier, he did not have a copy of it. It was his original paper from 1980, where he gave this correction for these ping pong ball size globe thermometers. In fact, this measurement of the correction, which is still in the ASHRAE Fundamentals Handbook and is still part of the mean radiant temperature definition on Wikipedia and is still in the ISO 7726 standard, is wrong, unfortunately, for the majority of cases that we use globes. And that's because when globes warm up in the environment, this is a plot on the left showing the free convection and the forced convection value. So a forced convection at 0.3 meters per second, which is pretty common in an indoor environment without fans on. Just to give you a rough sense of where it is, you can see that as soon as the globe temperature, this is the divergence between the globe and the air temperature on the x-axis here. Which button is it? Oh, there it is. Yeah, so this is the important variable for us, which is how much this is trying to get warmer than the air around it. And this is a Schlieren image just showing all the air movement that happens around it, because of course there is convection with this device. And the problem is actually that the free convection part becomes very significant. So it becomes a larger portion of the heat transfer. And in fact, most of the time, mean radiant temperature divergence are in this range of 1 to 2 degrees. And you're generally in this zone, which is what we would call a mixed convection zone, which is actually a harder version of convection to try and model and correct for. But you can. And what we found is that when we build a mixed convection model, the standard correction is exactly what we thought. So this is just a scatter plot. We did a very controlled experiment in Weimar, and they're similar to what you have in Perugia, a very controlled comfort chamber. And we modeled the real mean radiant temperature, and you can see that the globe fails to measure the real mean radiant temperatures on the line. And so you're consistently not measuring the actual divergence of radiant temperature to air temperature. But if we use a mixed convection model, we are able to get a more accurate correlation between the mean radiant temperature and the globe temperature. But what we found, more importantly, is these ones on the right are the ping pong balls, and you can see the amount of variation. Even with the mixed model, really the ping pong balls, frankly, are just pretty useless in the accuracy that they give in terms of the mean radiant temperature. You can do kind of okay with the 6-inch old toilet float, big globe, but when you go down to the, when you go down to these small ping pong ball size radiant temperature sensors, you really have an amount of air that is generally, if you have any air movement, it's largely swamped out by the resolution of your air velocity sensor, because remember, the correction for the forced part has to be done with high precision anemometers, and generally that air propagates onto the radiant temperature you're trying to discover. So in general, there's a significant problem. And when we took this and then looked at the ASHRAE thermal comfort database, a very commonly used tool with over 200,000 measurements, that there is statistically significant error for more than 10% of all of those points, the majority of which don't even have air movement measured. And so this is just kind of a heat map showing where all the values are. So as soon as you get above about 0.7 degrees around here, so all of the points from here up basically have air that's more than 100% of the reported value of the mean radiant temperature. So there's a significant problem with how we are measuring mean radiant temperature. In general, we are under-reporting the amount of mean radiant temperature deviation from air temperature. There's been some papers lately from colleagues that are reporting mean radiant temperature tends to be always the same as air temperature, but we're arguing that mean radiant temperature tends to be unreported as different from air temperature because the measurement devices are not measuring it properly. But lucky for you, just like at the end of The Good, the Bad, and Ugly, the good guy always wins, in theory, hopefully. And we have alternative methods, especially with Internet of Things, to measure mean radiant temperature in different ways. So we brought some of these. They're outside on the table outside. And I did a little very simple experiment just in my office so that I have an excuse to come to Calabria, which is shown on the bottom here, comparing the globe to what we call our cube sensor, which is just a series of probably the same device that Enrico reported having in his thing, this infrared temperature sensor. So that's these little guys on the sides of this here. And it measures the planar radiant temperature in each direction. And so this is the quick data set that I took in my office, just showing this is the red line is the reported mean radiant temperature from the globe, or recorded globe temperature. This is the air temperature in the room, the blue line. And then, well, sorry, the orange line is what was read by the globe. The red line is what the current correction would tell you the mean radiant temperature is. And then the flat line is our instantaneous measurement from the cube and from the model that we did of the room. So they are both, I didn't put the air bars, but there's about half a degree of air up or down on these. But you can see that they match well to the mixed convection model. But the more important thing to point out here, which I haven't mentioned yet, is that also when you're using globes, the settling time, one of the main reasons we switched to ping pong balls in the 80s was because it took so long to get a globe thermometer reading. The settling time of a globe is very, very long. So that's another problem, whereas these sensors have a 10 hertz refresh rate. So you can take 10 measurements a second, basically, with each of the sensors on the sides of the cube. And then moreover, the globe has no idea what's going on in any direction. And the globe also has localized heating that still happens that makes there be a significant amount of air. And with our cube sensor, we're able to detect this directional differentiation or radiant asymmetry that happens, which is also super important for thermal comfort and causes this whole separate aspect of thermal discomfort that can be from there being an asymmetry. Even if the mean radiant temperature is a perfect 20 degrees, you may have asymmetry that causes discomfort. So this is also a problem. There's like 40 degrees of asymmetry in this sort of quick and dirty experimental setup that I made in my office. The main takeaways from that quick experiment are that the globe, as is reported in the standards, this is one important thing the standards have right, is that the globe's air is plus or minus 2 degrees Celsius. So you can please go tell all your friends whenever they do globe experiments that don't put the resolution of the thermistor in the globe as the error. This common mistake where we put like plus or minus 0.1 degrees Celsius. The sensor can only measure plus or minus 2 degrees at the very best of the mean radiant temperature. There's a very long settling time. And then in the cube data, we were able to get good data that agreed with the mixed model. And that finally, there's still some issues, though, so the asymmetry we can detect. But the last piece, as we pointed in the paper, is that the edges of these sensors, when I have a cube and they overlap, there's still some issues in terms of understanding what happens when you have a point source of a very hot thing, and then it lands in between two sensors that are pointing in orthogonal directions. So there was some variation of about 0.2 degrees when we rotate the sensor through these areas. So like on the corners of this device, or on the corners of this device, if there's one very hot thing there, that can create some error in this methodology that we propose. And then I will just give a quick, very rough overview. So this is basically a quick presentation on the problem of measuring mean radiant temperature, and that we have an alternative way to measure just the mean radiant temperature and radiant asymmetry. But as Coleman is presenting in the next presentation in room A, we're also looking at how we can scan more precisely all of the surface temperatures in a room to model exactly what happens in space. So with all those experiments I showed earlier, it becomes super important relating to thermography that's also being presented in the other room, how you measure the surface temperature all around you at a very high resolution. So we've built a lot of different versions of sensors that do this kind of thing, and we brought this one, and Coleman's presenting it upstairs, which measures the shortwave and the long wave components in a full array of detectors. So it's basically making a thermal image that measures the watts of radiant heat in both the shortwave and long wave components. And we also have an array version of the cube sensor that doesn't just measure the directional temperature, but measures a full 360-degree thermal image. And from that, we can back calculate things like the mean radiant temperature distribution through space. So instead of one of the issues with mean radiant temperature is saying that if I measure my mean radiant temperature right here, over there by Marco, it could be 5 degrees cooler or warmer. And so if we have a map of the radiant temperature, we can measure those things. We can do this for old buildings like we have on Princeton, where we made maps of the whole surface temperature in the entire space and use that to direct people to where the room is warmer or colder in a way that air temperature sensors would not be able to measure by measuring this radiant temperature component. So we can make this map of where the room is actually warmer or colder by measuring all the surface temperatures. And so this sort of broader use of sensors sort of brings me to the bigger conclusion I would make in our session today about people, which is coming back to that argument of how can we use, in this case in particular, better physical measurements of variation in mean radiant temperature and radiant heat transfer to actually make people more comfortable in rooms. And not only that, of course, these sensors can sense people because we're warm. And so we can think about that feedback loop. And ideally, maybe some of these better sensors are things that we can use to potentially help, drive us in that direction of making people comfortable, not claiming to make rooms comfortable. So thank you so very much. Happy to take questions.
Thank you.
And please come back and we can discuss more over the break.
Yeah. Maybe just one question. Mm-hmm. Then if there are others, I will give. But what will be for you? We have seen for the globe, we have an error which is 2 degrees. Mm-hmm. What we can achieve with this kind of sensors? What is achievable for you?
So for the variation in space, you can be well below a degree, below half a degree, probably 0.2 degrees. So from one spot to another, just because the delta is very good, because all the problems that may arise from emissivity, which we heard a little bit about yesterday from Stefano when he was presenting thermography, emissivity will cause some more significant error even in our tools with the absolute value that we report. But if I want to know the variation in space, which is probably more important for people, like what I showed, the map of changing radiant heat transfer, that part I can know very precisely. I would argue to around 0.2 degrees or so from one spot to another. And then moreover, though, I'm also interested in avoiding using even the temperature metrics. I would much rather describe things in watts of heat transfer in space, because for me that becomes more interesting for how I measure a human body and exactly the change in watts and heat that people may be emitting, which comes back to sort of how much I can also measure your watts by understanding surface temperatures of you, which I think is another great reason to have this session where we're discussing skin temperature. And
yeah, exactly. Are there any other questions? Okay. If not, thanks. Thank you very much for a nice presentation, for really nice. So, move to the last work of this session, which is entitled Modeling the Thermal Response of the Human Body for Thermal Comfort Assessment in Indoor Spaces and Experimental Validation. The work comes from the colleagues from University of Naples and is presented by Giuseppe Russo. Please.
Okay. Good morning to everybody. My name is Giuseppe Russo, and I'm a PhD student at the University of Naples Federico II. And I'm going to present you a work focuses on an experimental validation of a model, of a developed model used for the assessment of physiological responses and thermal comfort of human body in indoor spaces. The objective of this work is to compare the impact of diverse proposed methodologies and also different modeling approaches to the thermal comfort of occupant and the associated building needs, and in particular heating and cooling needs. To this aim, I will present you the most important and aspect of the proposed methodology and the results of the case study analysis. As we all know, the fungus theory is widely adopted for the thermal comfort assessment in indoor spaces by solving the heat balance of a human body in steady state condition. But this theory shows several limitations, such as it considers people as passive sensors and neglects adaptation opportunities like physiological aspect and cultural aspect. For this reason, the objective of this work is to develop a thermal comfort model integrated in a building simulation tool for the assessment of building thermal needs. And also, the physiological thermal model allows for the resolution of human body temperature field in one-dimensional and in transient regime. The shape of the human body is assumed to be equal to that of a cylinder consisting of 4 layers: the core, the muscle, the fat, and the skin. And the geometrical and the thermal properties are evaluated thanks to the work of Fiala and of Stolwick. The heat generation term, represented by the metabolic rate, is present only in the core and the muscle layers, and also the heat dissipation is due to conduction between the adjacent layers, and also by convection with the blood perfusion and also with the surrounding environment. The novelty of this work is respect of the other thermal physiological model is to evaluate the metabolic rate of people in function of individual parameters, really the heart rate and the body weight. So in this way, we can assess the physiological thermal model and suitable to the investigated person. Also, thanks to core and the skin signal, we can assess the blood perfusion and the sweating rate. All the investigated thermal comfort approaches are implemented in an in-house building simulation tool called DETECT. This tool is based on finite difference method and solve the heat phenomena and the heat transfer phenomena in one-dimensional. Also, now we give an experimental validation of the human body thermal model. Thanks to a collaboration with the University of Perugia, according to NextCom project, it was possible to assess and test the result of the modeled human body. And the experimental work was carried out in a test cell room located in Perugia. And in this table, we can see the thermophysical characteristics of these buildings. Also, the thermal and hygrometrical parameters necessary to simulate the thermal interaction between the occupant and the surrounding environment was measured thanks to swearable sensor located near the workstation. And also, the heart rate and the other physiological parameters necessary to estimate the metabolic rate, as previously said, are evaluated thanks, as previously seen in other presentation, thanks to Empatica. Then in this slide, we can see a comparison between the mean skin temperature simulated and the mean skin temperature evaluated by Empatica sensors. And in particular, in the figure at top on the left, we can see with the blue line that the dynamic trend of mean skin temperature is quite similar to orange one. That is the value of mean skin temperature measured by the experimental work. And in particular, as we can see on the graph on the right, this percentage deviation is within the value of 3%. Also, in this last figure, there is the PMV trends evaluated with the measured and with the simulated skin temperature. And as we can see, the blue line and the orange line are very, very similar. And for this reason, we can say that our model assess in a good way the thermal comfort of occupants. Now, in this model, as depicted in this scheme, we develop a smart control strategies for the asset for guarantee the thermal comfort in indoor spaces, and taking in account the physiological parameters of human body. In this slide, there is a schematization of the adopted strategies. As first, we assume to know some physiological data, like the initial skin temperature and the heart rate measured thanks to wearable devices. And then, thanks to developed thermal simulation model of building called TETECT, it is possible to estimate some thermophysical characteristics, for example, the mean radiant temperature. After that, all these properties are known, it was assessed a double-step optimization. In the first step optimization, we determine all the possible combination of indoor air temperature and relative humidity that maximize the thermal comfort of people. And then, with a second step of this optimization, we can assess the optimal and the best solution, which also minimize the energy consumption. In this way, to propose and to compare the results of the proposed methodologies, a suitable case study that consider a single office space where the HVAC system is on from the 8 a.m. to 5 p.m. The air velocity is set and equal to 0.4 meters per second. And the simulations are carried out in the climate zone of Naples according to Meteonorm weather data files. Also, as regard the thermophysical and physiological characteristics of occupant, we assume that the initial condition of mean skin temperature is equal to 13.7 Celsius degree and a constant value of heart rate of 70 BPM. As previously said, we evaluate and estimate 3 different strategies to adopt and to control the indoor air temperature and relative humidity in indoor spaces to guarantee the thermal comfort of occupant and in the same way minimize the energy consumption. These 3 strategies were compared with this reference case of UNI standard, UNI 10339 standard, which conversely suggests seasonal set points and constant, really 20 Celsius degree during the winter season and 26 Celsius degree during the summer season. In this slide, we describe the optimization analysis that is adopted for all the proposed 3 strategies. The 3 strategies are based on 3 widely adopted indices, thermal comfort indices. Really, the PMV of Fanger, the DISC of Peirce theory, and TSV of Kansas University. In this slide, we can evaluate the first strategies related to PMV Fanger. And as previously said, at first, after that the physiological parameters are simulated by our physiological thermal model, it can be possible to evaluate all combination of indoor air temperature and relative humidity that maximize the thermal comfort. And then, in red circle, after the second step of optimization, we choose for the current time step the optimal temperature and relative humidity to be set. This analysis and these processes is iterated for all time step in which the occupant are in the building. And also, thanks to human body thermal model, we can predict the physiological parameters in the next time step. The same analysis was adopted also for the other two strategies, as said. This strategies is referred to disk of the disk index of Pierce, and this third is referred to TSV of Kansas University. Now we give some results of energetic and thermal comfort analysis. And but in this slide, we give at first a look to the recurrence of the set point, indoor air temperature, and the relative humidity that are mostly repeated during the simulations. And as we can see in the first strategies, for cooling needs, the indoor air temperature to be set mostly is 27 degrees. And with the third strategies, the mostly repeated value is 29 Celsius degree. This value we can be noted that are higher than the 26 Celsius degree for the reference case. And for this reason, we can assume that the energy consumption is reduced in this case. Now we give some information about the dynamic trend of thermal loads assessment for the first week of January for all the strategies investigated and for the reference case. As we can see from this figure, the reference case is the one that during this week required the minor heating needs. And conversely, the first strategy based on PMV Fanger is that one that required the most heating needs. The same analysis was repeated for the week of July during the summer season. And also in green line, we can see the dynamic trend of indoor air temperature to be set in order to guarantee the thermal comfort and minimize the energy consumption for all investigated strategies. Finally, an annual and monthly analysis of energy consumption for heating and cooling requirements is reported in these slides. And in this table, we can summarize the most important value obtained from this simulation model. In particular, we can see that all the proposed strategies guarantee the total comfort for the occupant during the heating and during the cooling season. But conversely, the reference case is represented by about 2,100 hours of discomfort of the occupant. The first two rows are referred to the value of energy consumption during a year for the investigated analysis and investigated buildings. And also we can note that the Fanger's dynamic control also to guarantee the most important results in order of thermal comfort of occupants for cooling demand is the strategies that required the minor energy consumption. In conclusion, we developed a non-uniform model of the human body based on thermal nodes for the assessment of physiological parameters in transient regime. And this human body, compared with some, as I said, with some experimental work related with the University of Perugia, we assess also this physiological model and implemented this model in a building simulation tool for the assessment of optimal indoor air temperature and relative humidity to be set. And in this way, we can do an analysis of the heating and cooling demands. And as previously seen, great results are obtained in terms of energy savings. And thanks for your attention. That's all.
Thank you. Questions? Please.
Okay. Yes. Yes, I say that it is a mean value because it is measured in function of 10 points. For example, on the head, on the arms, on the legs, and all the points where this measure is evaluated and assessed. After this measure, we have a weighted factor, a weighted mean, where, for example, the head is the body part that have the highest influence in terms of mean skin temperature, for example. So, yes, we evaluate the mean skin temperature thanks to simulated the thermal interaction between the human body and the surrounding environment. Yes, I from different parts, but the novelty is that these heat fluxes, in particular the generation of human body, is evaluated in function of physiological parameters like the heart rate and the body weight. So we can evaluate the singularity of the occupant that we investigate. Yes. Yes, we after that we can simulate in this model the skin temperature and predict the skin temperature in the next time step in function of the all parameters set in the current time step. And in function of the predict skin temperature for the next time step, we can evaluate and the optimal indoor air set point to be set in function of the physiological parameters investigated and predicted for the next time step. So to rank the thermal comfort of occupant and at the same time minimize the energy consumption.
Probably just to create a link, maybe because to calculate the temperature of the skin, you need to calculate the heat balance. So probably the link with what Forrest was saying before, that maybe you can use the same model, not using just this simplified, let's say the common approach using temperatures and psychrometric chart, but using the same model,
yes,
with a different approach, which is based on the energy exchange, so on watts. So probably this is the link that can be created for sure.
Yes.
Rather than trying to fit into all empirical, I think you also have to
Yes. Yeah. In fact, our
like
when you step
yes, in the at the entrance.
Yeah, there's the inertia. Yeah. But then when you go in the balance, that's not so cool, because then in that case you are in the balance. So this is how it can be used. Right? So thank you very much.
Thank you.
I think we can close this session. It's time for having the light lunch, which is outside. Also especially thanks to those who remain until the end of this session. Thank you. Have a nice day.
thermal measurement. And it's a very big honor for me to chair this session, which is entitled Measurement Techniques and Procedures for Quick and Emergency Diagnostics of Buildings. And you will see that all the papers and presentation will be devoted to exploit the aspects of measurement could be useful for measuring in emergency and fast recovery situations. So we will have 15 minutes for presentation and about 5 minutes for questions and comments after each presentation, each talk. And I invite myself, which will be the next speaker, but also the speaker of the session, to respect this time scheduling. So we will move to the first talk, which is entitled The Calibration Issues of a Total Station for the Assessment of Buildings in Emergency Conditions. And the authors are Giulio De Miria, myself, and Emanuele Natale from University of L'Aquila, Antonella Gasperi from Polytechnic of Bari, Stefano Marcella and Marcello Marzoli from the Corpo Nazionale dei Vigili del Fuoco in Italy. I will move to my place of presenter. We will move directly to the introduction. The topic. We want to evaluate the level of damage of structures after an earthquake, which is the situation we want to face with. To support the logistics of the rescue and operate safely, to implement provisional measures able to secure buildings, in particular the cultural heritage, and of course, for these aims, the use of measurement instrumentation could be a useful support to improving efficiency of intervention and objectivity of the assessment. So it's not a measure to obtain the best data as possible, as much as possible, but to support the emergency intervention, which is a requirement to be satisfied. Standardization of procedures of assessment, taking into account also that we are in a situation of the emergency state. For instance, we could be unable to assess or to assess continuously some measurement points, or we need to operate in the shortest possible time, depending of the fact that we don't know how much it saves the structure. Also, the possibility of accidental voluntary movements of the instruments due to the sudden needs in emergency conditions. So, to specify the metrological aims of the work, we want to do a metrological evaluation of a total station in field, taking into account the operational constraints imposed by an emergency situation. And we also want to evaluate the effect of simplifying the choice of monitoring points on the assessment of the same characteristic of building that could be interesting. For instance, the slope of a facade of a building. And this analysis intended to be a preliminary contribution toward the standardization of procedure for the adoption of the total stations in emergency assessment activity. please let me give some idea about materials and methods. In this paper, we used as the measuring instrumentation a total station by Leica Geosystems. In particular, the model is TS16 imaging. And the measurement we will describe refer to a building which is an old building in a village which is been interested by the earthquake of L'Aquila in 2009. You can see that we got on this facet about 13 monitoring points. You can see the layout of the measuring network. Of course, we used the target points in the monitoring points, and you can see in the you can see also the reference point, which are useful to set the reference system for the measurements. So these are the target points when we want to do measurements. For instance, from number 1 to number 13, and these targets are used to set the reference for the localization of the measuring points. Which is the analysis we did with reference to the measured data. First of all, variability between measurements obtained within a few days, the so-called repeatability of measurements. But also we repeated measurements during a very long periods, also 1 year away, in order to test the reproducibility of measurements. Also, we want to assess the possibility of the system to acknowledge the existence of very little displacement we simulated by thickness we glued to the facade in order to have calibrated displacement of the measuring point. Another aspect we studied in order to satisfy the requirement of possibility of using simplified procedure, we also studied the possibility of reducing the measuring points, and we also studied the effect of reducing points depending on position of points we are taking into account, also depending on their number. This could be useful when we want to take in an emergency condition very, very quick measurements in order to get reliable results. And please let me give you some preliminary results, which are anyway interesting. Repeatability and reproducibility of results. Repeatability when we repeated the measurements during 1 day, and reproducibility when the interval we considered is 1 year, which is the data we considered. The main difference of the measured distance between the points with respect to the reference 1, which is in the range of plus minus 2.1 millimeter. That means the distance of points with respect to the reference point when we repeated measurements is in the range plus minus 2 millimeters. And the standard deviation of these differences is 1.4 millimeters. We also considered the repeatability of the facade vertical inclination, which is in the order the 4 seconds of degree. Of course, in case of reproducibility test, when we consider an interval very, very long, 1 year for the precision, we found a similar difference between measurements which are done at the time difference of 1 year, which is in the order of 2 millimeters. The standard deviation is slightly increased 2 millimeters. And also the reproducibility of the inclination is enlarged. 30 degrees is the value we measured. So this measurement suggests thus that the threshold we can assess a displacement is in the order of a few millimeters. So the question is, how little is this threshold? If we consider an imposed displacement, are we able to assess it? When we considered a thickness of 4 millimeters, and our question is it the system able to acknowledge it? But this is the result with reference to the 13 monitoring points. The mean is a little bit less than 4 millimeters, 3.5, with a standard deviation in the order the 1.5 millimeters. So if we consider the results on the whole, it is confirmed that 2-3 millimeters of displacement could be the minimum threshold that could be considered for this approach. Well, the last point we considered is simplifying the network of measuring points. We considered as the reference situation when we use all the points, and we considered many combinations of points to be taken into account, in particular 10 configurations. The best configurations are those we consider the point at the extreme points of the network. So, for instance, the configuration number 10 considers only 4 points, number 1, number 1, number 13, number 11, number 4, and you can see that results about inclination are very similar to the results obtained with all the points. So simplification with being careful could be done. I move to conclusions. In this work, a building has been used as a test case to assess the meteorological characteristics of total stationing field and to study simplified procedures for assessing the state of buildings in technical rescue operations. We want to assess repeatability and reproducibility of results for displacement and inclination measurements. And also, we used a target of no thickness in order to assess the possibility of a knowledge at minimal threshold of a few millimeters. And this has been confirmed by results. Also, some aspects are being studied with reference to the possibility of simplifying the network of measuring points. This is a first step in order to realize reliable but procedures for monitoring in emergency condition of buildings, but it's important step by step to assess the meteorological characteristics on what is done. Well, I finished, and the paper is now open for questions or discussion. Are there any questions in the audience? Please. If not, I had a comment by myself. Typically, meteorological performances of a total station are given by the producer. For instance, 1 millimeter of accuracy. But it is not clear in which conditions we can reach these performances. In the scientific literature, we got very good results. Accuracy is less than tenths of millimeters, but typically in emergency conditions, we cannot use laboratory procedures, people, and conditions. So it's important to assess performances in field. Thank you for presentation. Any more questions? No. If not, I move the second presentation, which is also by myself. The title is Assessment of the Provisional Structures Efficacy for the Conservation of Monuments After an Earthquake, Meteorological Evaluation. The approach is similar. The test case is similar too, but we use the different instruments. The authors are myself, Giulio D'Emilia, Luciano Giominto and Emanuela Natale from University of L'Aquila, and Marcello Marzoli and Stefano Parzella of the Ministry of Interior, Corpo Nazionale dei Vigili del Fuoco. The problem is similar to the problem I discussed above, but there are some differences depending on the instrument we want to use. And in case of laser scanner, which is the measuring equipment we use it in this work, we will expect some more detailed information about the building under examination. So we want to study also the behavior and the reliability of information during the time, depending on the way we use the data we got. In this case, we used the laser scanner, which of urgent technical rescue, thanks of its characteristics, in particular resolution of displacement and measurement accuracy, ease of use, relatively low cost. Also, the acquisition and processing time is not so high. And this is important in case of emergency intervention, the possibility to measure at a safe distance. Of course, to have data which are reliable, the system should be calibrated before use. But in case of emergency, very special circumstances can arise in emergency scenarios, and it is difficult to respect all the requirements we use it in calibration. So, for instance, we need to act as soon as possible. There is the probability of voluntary or accidental movements of the instruments. Sometimes it's impossible to acquire all the points of interest, especially we experimented the lower ones due to the continuous movement of vehicles and people. So the understanding how much simplifying procedure or using the system in difficult conditions could be useful. We, as I said before, we got information from scientific literature about the calibration and metrological performances of a laser scanner. I repeat, we can detect movement with an accuracy of some millimeter values. So some tens of millimeters is an accuracy we can achieve in laboratory conditions. Similarly, for laser scanning, Leica propose an accuracy of about 1 millimeter, but it's important for us to understand which is metrological behavior for in-field application by people which is interested to monitor and building as soon as possible, which is involved more in rescue than in measurements. So that's important to understand when people involved in rescue intervention use these instruments. In the picture, we can see the targets, which are the same of the paper before. it is to be highlighted that in the previous work we told about a total station. Now we used a laser scanning system. In particular, the system is Leica RTC 360 3D laser scanner, used by people involved in effective and real intervention of the rescue in emergency conditions. The building we monitored the same as before, 13 monitoring points with targets which are glued to the facade. But now we don't have one measured point. We got a cloud, and we studied the behavior of points which are located in the target, which are located around the target, directly on the facade. The software used for data processing is Leica Cyclone 3DR. And you can see the way the data are presented. We, by interfacing this data, we processed data which have been provided by this software in order to do the processing we will show shortly. Also in this case, we got a repeatability test. In particular, measurement which have been done in the same day, and all the points have been studied. We reference to two data acquisition. In particular, we did a previous acquisition we call acquisition number 1, and we did two different acquisition, number 2 and number 3, in order to understand some possible differences in data processing results. And also, we can choose 20 points for each target. And we considered the difference of distances we measured before and after the application of the thickness of no value. Let me go to the results. It's interesting that if we consider one reference acquisition number 1, and two different acquisitions which are taken in the same day, we can see that we got two interesting results. That the mean of the distance is different with respect to the point before the of reference. In particular, if I consider the mean difference of the position of the 13 targets at acquisition number 2 and number 3 to be compared with acquisition number 1, we can see that the average difference are in the first case 1.6 millimeter, in the second 0.44 millimeters. So there is also a little difference in the average difference. Well, also, we consider this difference. That means when the system fits the cloud points you measured, the obtained plan of interpolation is quite different. So depending on this fitting are different the averaged means and also the standard deviation. Well, the repeatability of measurements is in the order of 1 millimeter. When we insert the thickness, which is a thickness of 4 millimeters, we obtained results like this. In particular, in the first case, the mean difference 4.2 millimeters with a standard deviation among targets of 0.22 millimeter. And in the second measurement, the mean difference is in the order 4.9 millimeters with the standard deviation being 0.52 millimeters. So, which is the summary of results. We got, depending on the way the data are processed, a random variability of the systematic differences, which is in the order of the very few millimeter, 1, 2 millimeter. And also we got a standard deviation results of the same entity, 1 millimeter. So, if I go to the conclusion, laser scanner could be used for assessing of buildings in technical rescue operation. It's important to evaluate in field its behavior. In laboratory condition, we get accuracy in the order of tens of millimeter. In the producer says that there is accuracy 1 millimeter. And in field, we found that there is two components contributing to the uncertainty. The first one is related to the fitting of data that produces a difference in the mean difference of the point. The second one is related to the variability around this plane of fitting. But the final results is that a difference in positioning of 4 millimeters due to the insertion of a real thickness, having this thickness, will be easily detected. So uncertainty in the order 1-2 millimeters could be reached also in field conditions. Thank you. Again, the paper is open for discussion, comments, or questions. Please. Yeah. Of course, result depends on many aspects, and we found that there is a difference from the points taken on the targets and on the facade itself. So. But also the geometry is important. But also, according to the result I discussed in the previous talk, we can see that general guidelines could be set. That means a minimum number of measuring points, a minimum number of repetition of the measuring loop, and also it's important to pay attention to the data processing, but some general guidelines could be obtained. Thank you to you. Any more questions? Well, if not, I move to the third presentation. This is a notice, is not by myself. And the next paper is entitled Ensuring Safety of Cultural Heritage Experts while Safeguarding Historical Buildings. The 3D survey of the Sacro Convento di Assisi as benchmark to test innovative emergency management procedures. And the paper is by Stefano Marcella and Marcello Marzoli and Danilo Anastasi of the Corpo Nazionale dei Vigili del Fuoco. The paper will be presented by Marcello Marzoli. Please, Marcello, the stage is yours.
Good afternoon. Well, this is our presentation of probably one of the first work we made, even if it was finished some time ago, regarding using laser scanner in particular. And yes, well, why we started? We started because we had some difficulties, you know, in particular with earthquakes. the last two earthquakes, or no, not the last two, well, quite often we have replicas of earthquakes, which means that the assessment of safety of buildings has to be repeated quite often, even only at the distance of a couple of months. And this it's quite problematic because you know, that we have some, together with the Italian Civil Protection, of course, some 1,000 engineers going around the area like L'Aquila or like in Amatrice to assess buildings, and then repeating the same process after 2-3 months is really a big burden. So we were looking for solutions for something which can help in being more efficient. And here in particular, we wanted to see we had the same targets which were stated by the professor to in particular to assess the safety of the buildings when we are operating, like for the case of the total station, so a continuous measuring during the rescue operation. And then on the opposite, there were separated different scan of the same building in separated in time. So before or after the first shoring structure are placed, and then after a while to assess if the shoring structures, the provisional structures were efficient enough. For example, you can see here the church of the Basilica of San Benedetto in Norcia, and which unfortunately was only the facade was left, and of course it was quite problematic to stabilize. What was the problem at stake? The problem was, well, we have now, you know, in Italy, quite a good civil protection system where we cooperate strictly. And for historical buildings, there is quite a clear regulation that, of course, cultural heritage expert has to decide and assess the problem and decide the provisional structure to use. On the other hand, when there is an unsafe area, like a red area, as we call it, then by the law, only firefighters can enter and decide how to operate in safe conditions. But this opens a problem. When you are inside the church, inside the basilics, then this problem was open exactly in Assisi. You will recall most probably the Giotto paintings collapse I think in 1997, where I think 3 people died. Well, in that situation, I didn't write down because it could be, the history can be embarrassing sometimes. But in that situation, we had inside the friar, which was the owner of the site, and the expert from the Ministry of Cultural Heritage. So we had the experts inside. And there was even one firefighter who was even low rank, just inside the church. But he was thinking he was not responsible of the safety of those people, because they were more expert than him. But the judge decided on the opposite. When they died, it was decided that the firefighter was responsible, even if inside they were experts. Inside the church, there was both the owner and the expert. So we had a big problem, because in that situation, we should have experts, cultural heritage experts inside a building to decide the best provisional measure, but then they cannot enter because there are not safety conditions. That's the dilemma we had. So we were trying to look how to find a solution. We could put together these problems and provide a solution. So we started the research line in 2016 with some European projects. They are all here. They are all together, but they were in line. We used all of them since 2016. Then the other started in prep. Started in 2019. Strategy is still ongoing project on standardization, and all of them touch this kind of situation. We used this funding for these, of course, institutional problems. You can see here exactly to exemplify what were the procedure in L'Aquila. The professor recall very well because he was one of the actors in this case. I think it is San Domenico, this one. You see that the cooperation between the cultural heritage expert appointed by the Minister of Culture was normally a professor from a university or for some expert within the Sovrintendenza. And of course, they had to cooperate with firefighters for the implementation of the shoring structure. They were working on pictures, like you can see there. They took a picture of the damaged buildings, and then they were drafting the structure. As you can see, the results is very much compliant with the design which was made anyhow. But of course, I think it was quite clear we could be something better than designing, drafting on a picture. And adding the third dimension, of course. This was the idea. So we started. Sorry, I forgot to tell that we had one memorandum of understanding with the Sovrintendenza in L'Aquila and an agreement with the University of L'Aquila before with the regional directorate and now with the central directorate, exactly to validate this kind of procedures. And then we signed even another memorandum of understanding with the Sacro Convento itself of Assisi. Probably all of them has been there. Is a beautiful and huge structure with a lot of stratification of buildings and vaults and nicks. And it is why we put quite an effort in scanning the structure, because we wanted to understand from our point of view as firefighters, what were the operational problems, what were the problems to retrieve a full 3D of a complex building when you have to. It is well represented because you see there is everything inside. There are brick, timbers, frescoes, and painting status, everything inside. So it can represent quite well what we can find after a quake. Unfortunately, in Italy, almost always the cultural heritage is damaged. We used this instrument, always the Leica RTC 360. We made, this is important, very high number of scans of scannings, because we had hundreds of rooms. Because what you see normally you see the upper basilica and the lower basilica here, but you have to think to all the monastery, so all the places where they live and they act every day, which is very, very large, and it comes from San Francisco up to now. It's a very, there are the original, I think, 200, 100, 200, and then up to now it is 800-year-old. And then we had to make, of course, quite an extensive data processing to eliminate reflection, diffraction effects, which are quite common, in particular when you cannot select the place you have to scan. And then to link everything. We completed the work with the geodetic frameware network of 18 fiducial points taken with GPS RTK and using all the satellites, having quite a good reference system at the end where to place the scanning inside, outside the sacred convent. At the end, of course, for us as firefighters, was important to start to understand the process completely in a very demanding situation, so as to understand, and we understood the importance of design the assessment towards the targets of the assessment itself. So not to waste resources in too detailed scanning if it is not necessary. In this case, it was because we wanted to leave the scan to the Sacro Convento as a 3D picture in time, which can be used in the future. Hopefully, it will not be needed, but if needed, to reconstruct or to rebuild what it will be needed in case of earthquake in future cases. In particular, I think it's possible. It was they had a similar luck in Notre Dame when it got on fire, the roof, and they were able to rebuild it thanks to a 3D scanning they made before. So, of course, the value of the cloud is multi-purpose. It's very important for them too, for the Sacro Convento. What were the difficulties? Of course, in this case, having as a target the structural integrity, then the density of points and the quality of pictures had to be high. And but on the opposite, as you can see here, the shapes of the historical buildings are very complex. They are not squares, but they are a lot of niche, cellars, private areas, and so we had to go in very complex, intricate areas. This was the purpose. You can see here what you see here is a part of the Storm project. It is a part of the Terme di Diocleziano in Rome. Is the Aula 1, is the first room where we simulated that how it is possible having a scan of the site, making a scan of the site after the damage, to highlight and uploading in the cloud how it is possible to work remotely with the other experts, so without being in the same place, and so in a way giving a solution to the problem I was citing before. So how to have the experts working and deciding, the cultural heritage experts deciding in an unsafe area and deciding how to make it safe. Well, in this way, thanks to a 3D scan, we can work remotely, but in a measurable cloud of points, even if it is in a safe area and in front of a laptop. So this is to see the difficulties even in positioning the laser scanner. You see here, of course, there were, if you look for a structural integrity, you cannot go only in beautiful places, but you have to go whenever, under the roof and whatever you have to go. And sometimes you have to cover very high, very different aids. Here there are some numbers, quite an extensive, you see 2,300 scans, a lot of billions of points. Yes, finished, thank you. And you see 270 person days. So it was really an effort. Of course, it cannot be made again every time because it was an effort. But for us, it remains a unicum in itself. But it was very useful to understand because it forced us to to use to dimension the hardware, the architecture, and identifying the best software to manipulate this kind of data. I don't know what. Okay. There is some problem. Okay. I think it's some problem with the PDF, probably. Okay. No, è l'ultimo. Okay. Well, we can. We can. I was out of time, so it is not a problem. What, as a conclusion, was that of course it was quite an extensive problem. It was quite a big work, but we learned a lot from it, and so it's okay for now. If you.
Thank you, Marcello Marzoli, for an interesting presentation. The talk is now open for discussion. Any questions for the audience on the floor? If not, please let me give a comment which is related to the question of the talk before also. In effect, you showed that difficulties in assessing of the methodological characteristics of the procedures depends on many aspects, which is dimension of the building, typology, difficulties, and so on. So maybe a step-by-step procedure could be useful, I think.
Yeah. Yes.
Do you agree?
Yeah. Yes. Of course. We wanted to go to a very large building altogether. We had that opportunity that we wanted to see the difficulties by ourselves. It was useful as a learning process, but now luckily we are systematizing this process, even together with the University of L'Aquila, to make it more operational and useful.
Thank you. Any more questions? If not, we can move to the next presentation, which is given this one also by Marcello Marzoli. And the title is Use of Laser Scan and Total Station Systems in Fire Resistance Test of a Closing Element.
I was checking it works.
I think it's better by PowerPoint.
Actually.
Ok, sì. Va bene. No. Please, Marcello, the floor is yours.
Thank you. Well, this paper was had to be presented by a colleague of mine. Unfortunately, it was not here. It was. There are 5 authors. I could put only 3 here: Bonfatti, Lombardini, and Marzoli. These 2 colleagues are the managers of the Centro Studi Esperienze. Is a laboratory structure we have inside the firefighters, in particular for fire prevention activities. You can see within the Center of Studies Experience in the firefighters, we have one of the targets of the aims of this is to continue to evaluate the methodologies and tools to be used in the laboratory activities, in particular with the fire resistance test. In this case, we will present a fire resistance test of a door, where the novelty in this case, we have, of course, a quite well-established test procedure, which has to be valid compliant with the standards and the law, of course, even to certificate or to assess the proper certification of a door, of fire resistance of a structure. In this case, we wanted to check if using the same system, the laser scanner and total station, was useful to assess the warping of the door, which is one of the things we have to measure when making this kind of test. I'm sorry for it is a very it's not a beautiful slide, but what we have it is mainly regulation. Of course, testing fire resistant test is mainly regarding standards and regulation. So I think probably this is yes. Okay, we had to use this. You can see the standards and so that we have to be compliant with, and the decree of Ministry of Interior to where we have to apply to implement when making this kind of test. You cannot see here the door was deleted, but it was there. This is what you can see. It's the support of the door. Before probably you have seen behind. You can see the oven, the mouth of the oven, and this is the structure which has to be built in a very specific way to ensure it does not impact on the door itself. So it cannot contribute to the door itself. You can see it is a quite a rigid structure made of steel, which support the wall which is built on purpose to support the test, so as to replicate the real condition as soon as much as possible. To carry out the test, you see the oven where there is, of course, there is a description of the oven. It's quite large. It's 3 meters per 3 meters, and it is 1 meter and 20 centimeters deep. There are instruments inside, flame burners, and there are reading points for pressures and temperatures in different ways, with the reading system, of course, in background. And the door, the structure, the door which has to be tested for fire resistance has to be placed with the less resistant part towards the fire. This is how it is prescribed by the law. So in this case, where there are the hinges, then. What we were measuring, apart from the temperature monitoring, we used the standard procedure, and we used even for the displacement orthogonal to the door plane to see the deformation, and so the loss of structural integrity and the potentiality that of course the smoke and the heat can come out. We used, of course, the standard instruments, which were wire-based, but we used too this total station-like TS16, monitoring the same points we were monitoring for temperature. And the oven is, of course, follow a standard load curve of temperature, which is prescribed by the law. outside the structure, the temperature had to remain, of course, at 25 degrees. This is the total station which was automatically following the same pattern over and over, the same 14 points. And we used to register the points and a system, a software, which we call it Safer, which is built on purpose for us, not for this reason, honestly. It was to see if it was possible to use for the safety of firefighters during emergency conditions, to assess the stability of a structure where the rescuers are operating. In this case, the user was very similar. You can see here how it was possible to see on the right. There were the displacement in centimeters and of the doors, and you can see that the door during when the fire is on behind is like a breathing, so it is oscillating up and down, releasing the heat and then coming down to the original position up to when it collapses. And this is, of course, where the test is failed. The test fails when the door collapses, of course, when it is not more possible to keep the heat and the smoke in one only side. In this case, it should have resisted 60 minutes. You see that in 23 minutes it collapsed, and it was the test failed for one of the prescribed failure which was planned, which is the presence of flame outside of the door. But even at the same at the same moment, we measured with the safer system and the total station. You can see the 14 points oscillations up and down, and then you can see very easily at the end when the deformation became plastic. It does collapse, and so there is no more keeping of the heat inside. Reaching, of course, before it was between 1 centimeter and 1.5 centimeters, and then it was reaching 2 centimeters and a half when the test was terminated. Of course, we measured even after, and you can see the temperature over time, which was, you see there are some degradation. It was even more difficult to read. Determination, you see here the criterion the criteria to terminate the test. They are quite very large. If there are slots opened, if there is ignition of a cotton slab outside, so the thermal is not keeping the thermic inside, and then the increase of temperature, everything was within parameters. The first to fail was the flame outside, which was exited from the door. At the same time, we used even the laser scanning system. We were using again to understand better what was the best tool to use. We were retrieving continuously cloud of points of the same door for a later comparison between one and the other. And here you can see the comparison between one of the scans made at the start and the other at the end, and you can see very easily that where it collapsed, where there was the collapsing in the upper right corner, with a clear warping of the door. This was the result we had instead with the total station. Whereas this one was taken after, of course, we have a continuous measuring of millions of points all around, and so we can have a good comparison after the test. With the data station, with the safer system, the good point was that we had this assessment of only 14 points, but continuously, in real time. We could see the evolution of the door warping in real time. And you can see how it was depicted, the collapse. At the end, it's very clear when it collapsed completely the door. You can see here, just for notes, what were the events which were registered over time, and the minutes where it was, and you can see that, of course, the minute 26 was the one where the test was terminated, and then we continuously took note even after the oven was switched off. So what we took that we had very good results. Operating a total station, it is not needed, of course, both, but the total station could be enough. It's very interesting because it does not require to interact with the door, with the sample. We can work from outside without any possible interaction with the door sample. And so, and the outcomes are very, very clear and really easy to read. I think this is all. This time I was.
Thank you, Engineer Marzoli, for very interesting presentation. You are exactly in time, so this is another quality of your talk. And the paper is now open for questions. Are there questions in the audience? Well, if not, please let me ask one question to me. You, in conclusions, you gave some motivation using these instruments, but in your opinion, measurements by total station or laser scanning could be used for contemporaneous measurement of building stability and fire effect of fire, both for doors and building on the whole?
Well, we see these instruments as a tool. It's a very flexible tool. It's a very, very interesting tool which can be used for a lot of things. Now in the forensic area is very clear because of course the Polizia Scientifica and the Carabinieri are using every day, and we too are using laser scanner for forensic, but it can be used for a very wide spectrum of cases, and we are exploring these. And of course, in this case in particular, we have to always to be aware that if a test has to be valid, has to be blessed beforehand by the scientific community, of course. So we use it in an experimental way, but as soon as we know it can be accepted, we will, of course, use it continuously. Thank you.
Thank you. Any more questions? We are in time, so there is the time for one more question, if possible. Well, if not, please let me close this session. We was entitled "The Measurement Techniques and Procedures for Quick and Emergency Diagnostics of Buildings." Please let me thank the speakers, but also the audience for attention to this talk. I think that the most important message is that people which is involved in true safety and rescue application needs to cooperate with the scientific people in order to get reliable procedures and use of measurements for their operation. So thank you for attending this session, and now it's time for coffee break, if I well understood.
everyone. I am Domenico Tomassa from the Polytechnic University of Bari, and thank you for coming here today, and welcome to this special session titled The Change of Resilient Structure from Traditional Approaches to Internet of Things and Structural Health Monitoring. In short, this session is focused on investigations about new opportunities offered from digitalization to structural health monitoring of structures and infrastructures. And in particular, this session concerns contribution regarding risk reduction for resilience, innovative assessment procedures of structures, real-time structural health monitoring of infrastructure, and big data processing and the Internet of Things. I briefly recall the presentation guidelines. The duration of each presentation is 20 minutes, including discussion, and authors should limit their presentation to 15 minutes to allow for 5 minutes of questions. So now we can start the session. Today we have 4 contributions because the first contribution listed in the program have been withdrawn. So let's move to the second contribution. The authors of this work are Elisa Bertolesi, Mario Fagone, Ernesto Grande, Gabriele Milani, and Tommaso Roturno. The title is Innovative Fiber Optic Sensor Monitoring of the Lamination Phenomenon for FLCM Reinforced Carved Masonry Pillars. The speaker is Gabriele Minari, so thank you for being here. The floor is yours.
Thank you, Mr. Chairman, for your kind presentation, and let's go directly to the first slide. As you mentioned here, the work done is a collaboration, a joint collaboration among different universities. The first one is the University Guglielmo Marconi, Telematic University in Italy, then Brunel University in London, United Kingdom, then my university is Politecnico di Milano, and then the University of Florence. A brief overview here of the presentation. So first of all, we will address the importance of the problem, and then we will discuss a little bit regarding the importance of fiber optic sensoring, and then we will show some preliminary experimental results on a coupon and on a single lab shear test carried out on a flat masonry pillar. And then we will present the results of a numerical model that is basically based on a spring model with shear and axial springs, finite element model, plus an analytical formulation. And then we will go in the end to illustrate some future developments that is an ongoing research. So let's go, first of all, in this slide to highlight what is the importance of the problem. Here on the left, you see that there is a reinforced masonry arch. Typically, the reinforced masonry arch face for the formation of 4 flexural hinges. You can see the red circles here for the application of a concentrated load on the quarter span on the left. And the importance of the problem stands on the fact that such kind of structures, so masonry structures in general, are particularly vulnerable to external concentrated loads and also seismic loads, because masonry is unable to withstand tensile stresses. As a matter of fact, one of the most effective modeling approaches is the utilization of the so-called no-tension material. And then for limiting the analysis to masonry arches, it is important to highlight that the behavior of a particular subclass of masonry arches is the so-called problem of skew masonry arches. So when we have a geometry that is irregular, so geometry that exhibits a certain skewness, then the modeling approach and also the prediction of the load-bearing capacity and also the active failure mechanism is not an easy task. And then we have also to highlight that in practical cases we can deal with slender masonry arches and also squat masonry arches, where we can have also the activation of out-of-plane sliding. That is quite a tricky issue.
especially in presence of the action of point loads as it is represented in the figure. And in general, if we follow the so-called Hyman approach, the behavior of an arch is a behavior that can be modeled with the concept of the so-called inverse catenary. When we apply a TRM, a textile reinforced mortar, or a fiber reinforced cementitious matrix on a mesory structural element, so we apply a matrix that is an inorganic matrix, typically is a mortar with a high tensile strength, and then we apply a fabric in form of grids. Such fabric can be of different kinds, can be realized with different kind of materials, and then we finish the work with an external plaster just to sandwich this fabric between the two matrix layers. And the behavior of the arch under the external loads is totally different with respect to the reinforced case, because we have the problem that is represented on the picture on the bottom right. So we have the delamination or the debonding process of the reinforced pack to the substrate, and is the bonding process that is typically fragile. So let's go now to analyze which kind of fabric we can sandwich between the two external and internal mortar layers. So you can see here a detail of the fiber reinforced cementitious matrix strengthening system. We can have different materials. For instance, we can have carbon to realize the grid. We can have PBO also, FRCM. We can have aramidic glass, that is this grid that you can see in the center. We can have also steel. SRG stands for steel reinforced grout. But we can also basalt, and in case of basalt, so we call FRCM as a particular typology of a strengthening that is called BTRM, so basalt textile reinforced matrix. We have also some guidelines that are provided by the Italian National Research Council, and they provided a technical document that is called Technical Document 215, and it was then published in 2018, so very recently, for steel reinforced grout. So let's go to analyze now the experimental procedure that we followed. So the problem in the fiber reinforced cementitious matrix reinforcement is the fact that if we wanted to measure strains on the reinforced grid, so it is not an easy task. So we have to use some methodologies that go beyond the traditional methods using strain gauges. So one idea is to use optical fibers. The technique is theoretically, at least in principle, quite simple, because we use an optical fiber. So the light beam that is typically a laser is sent down an optical fiber toward the gauge lens, and then the light waves measure changes in state. So they can measure elongations and also contractions of the rope. So the change in reflected light waves is therefore correlated to the local strain reading. And then we have also a machine that demodulates the reads and the light signals and give the voltage. And then we have also a data acquisition system that is called DAS, using an acronym that converts the voltage to strain data for then data reduction of the experimental strain measured. So the collection of raw data on strains is therefore crucial to set correctly a bond slip law. So why it is important to measure experimentally the strains? It is important to then evaluate the bond slip law that then is crucial to estimate the load carrying capacity of such structural elements in presence of fiber reinforced cementitious matrix reinforcement. So the selection of the sensors not an easy task because must be appropriate and robust, and we have to measure for, as far as the experimentation that we carried out at the University of Florence, short-term monitoring, okay, but the problem is that the strains are not visible inside the reinforcement because of the fact we have the plaster made by the high-strength mortar layer that is put externally to the reinforcing pack. So one of the crucial aspects of this is that we want to measure the interface local strains. So if we do some considerations, some theoretical considerations on the behavior of the reinforcing grid that is typically assumed as elastic, so the bundles of the reinforcement are assumed elastic, so we are able, as we will see during this presentation, we can have an estimation of the bond slip law. So if we go to analyze in detail the system, the experimental system that we used, so we used a fiber sensor that is placed, is glued directly to the reinforced grid, and we cut with micro cuts, with 6 micro cuts, these fiber sensors, so in order to obtain a discontinuity of the transmission of the light inside the fiber sensor, so in 6 equistepped positions, in order to then experimentally measure the strains on the fiber reinforcing layer, so on the fiber grid. So then we collect such data, such experimental data on a data acquisition system that is made typically on site. And this is done typically with a fiber optic dynamic interrogator. Then we will process the data automatically using a program, of course, of acquisition, of a data acquisition system, and the data processing is done automatically in real time by a computer that is located on site. In case, for instance, that we want to analyze a real structure, then we can process the data directly using a wireless technology in an office. So it is data processing, so the data reduction can be done also not on site, but also in another place using IoT technology. So the local strain measure, as I mentioned, is done in the fiber on 6 finite points. So here you can see basically the strategy that we used to evaluate the interface tangent stress that acts at the interface between the mortar layer, internal mortar layer, and the reinforced grid. So is deduced simply by equilibrium equations, as we will see later on during the presentation. So the slip is deduced directly from the experimentation integrating the strains that are read by the fiber optic sensoring system. And the hypothesis, as I have already mentioned, is that the fiber grid is elastic, and the support, so the measuring material that is under the strengthening system, is supposed rigid and infinitely resistant. And here you are the example of the coupon. So we consider the coupon made with the fiber reinforced cementitious matrix strengthening system is a coupon that is long 50 centimeters. Okay, we have 2 areas near the boundaries that are devoted to the experimental equipment to actually load the coupon. Here you are a detail of the fiber optic sensor, is this one, that is glued directly to the PBO strengthening grid. And here you are another detail on the bottom right of the construction of the coupon in the laboratory. So this is the experimental setup. As you can see, this is the coupon, and then we loaded the coupon into this universal testing machine at the University of Florence under poor tension. So we loaded in this point the coupon and also on the other boundary, on the opposite boundary. Here you can find the detail of the position of the 6 cuts that we obtained with the laser cut on the optic sensors and all the geometrical details of the coupon that was experimentally tested at the University of Florence. Here you are the global results. So on the graph on the left, you can see the experimental measure that we obtained. So on the vertical axis, you can find the stress that was measured experimentally, and on the horizontal axis, the experimentally measured strain. You can see different curves with different colors. They refer both to the readings that were obtained in the sensors and also the reading that were collected on 2 LVDTs as an average that were used, is the red curve, is this one, that they were used as control. And the typical behavior, experimental behavior of such coupons is that one that you can see on the graph on the right. So is a global behavior in terms of stress that is represented on the vertical axis and strain that is represented on the horizontal axis that exhibits 3 clear stages. So the first elastic stage where we have uncracked mortar layer and the elastic grid. Then we have an inelastic process in the second stage where some cracks for axial loads appear on the mortar layers, and then we have a final elastic or almost elastic stage that is the phase number 3 that is represented by the elasticity of the grid alone. And what we read during the experimentation is exactly the behavior that can be explained theoretically with so comparing the previous experimentation with the experimentation that we carried out at the University of Florence is they are perfectly superimposable. So we have a first elastic stage, then second processing phase with the damage of the layer, of the mortar layer, and then the last elastic stage of the FRCM alone. So let's go on now to analyze very quickly, because I am already out of time, the second example, that is the single lap shear test. So we tested with the same fiber optic sensor also a measuring pillar that is flat. So this is the experimental configuration. As you can see here, this is the fiber optic sensor. And these are the results. So the testing machine is this one. This is the results in terms of force, average slip that we measured experimentally, and this is the failure mechanism that we observed experimentally. So let's go to analyze the readings of the different sensors in the fiber optic. So this reading is exactly in agreement with some analytical approaches that we carried out in case of the fiber of FRP reinforcement. So we have a first elastic stage, and then progressively you see from these experimental readings that the reinforcing pack is detaching from the support, and this is perfectly in agreement with what we simulated using an analytical approach. And here you are then collecting the experimental results on the fiber optic sensor plus the considerations, the theoretical considerations that we already explained, the tau slip law that we obtained experimentally. So we can use this tau slip load and to put inside a finite element model that is basically constituted by an assemblage of in parallel and in series springs, nonlinear springs. So we can simulate also numerically the experimental debonding process using different interface law, for instance, an exponential one or a multilinear one. And here you are on the graph on the right, the comparison between the global experimental curve, that is this irregular one, and the analytical one, or the finite element one, that is represented by these more regular numerical curves. As you can see,
the agreement is quite satisfactory. So what's next? Next, there is a research that is ongoing. So we are doing the same experimentation. We are carrying on the same experimentation, but on curved mesory pillars in order to evaluate the debonding process, both experimentally and numerically or analytically on curved substrates in order to figure out what happens in case of reinforcement of an arch. So thank you very much for your attention.
Okay. Thank you for your interesting presentation. Okay. Are there any questions in the audience? Okay. If not, I have just curiosity.
Yes, please.
Yes. In the past, you or other authors have used this technology for monitoring also structures reinforced with the FRP? And if yes, there are some differences in this application, or
yes,
there are no differences?
Yeah, thank you for this interesting question, because yes, for FRP, yes, we carried out always in collaboration with the universities that I have mentioned, many experimentations on curved mesory pillars reinforced with FRP. The difference is the fact that on FRP reinforcement, then we can measure experimentally the strains simply using strain gauges. Whereas in this case, we cannot use strain gauges because the reinforcing system is different. So we can apply strain gauges on the FRP grid, but the problem is that the strain gauge is embedded inside the external mortar layer. So the risk is that the strain gauge either perturbates, let's say, the behavior of the strengthening system. So is what we observed is exactly this fact. So the fact that if we put strain gauges inside the FRP grid, then the risk is that the experimental results is a little bit scattered by the fact that we have the strain gauges that are applied directly on the grid. And the second is the fact that the FRP in that case is visible, so there is no need to use fiber optic sensors. So this is the second question. So the innovative part, let's say, of this experimentation is the fact that the problem is that the FRCM system is more complex, both experimentally and numerically and analytically, to simulate with respect to the FRP. So to find a global tau slip law is not an easy task. So I think that this is the major, advancement in the research related to the fact that there is a certain difference between FRP reinforcement and FRCM reinforcement.
Okay, thank you very much again. Thank you for your interesting presentation. Okay. Now you can move to the next work presented by Yu Yuan, Gabriel Stockdale, and Gabriele Milani. And the work is titled A Novel Fast and Low-Cost Masonry Monitoring Strategy for Masonry Arches. So Yu Yuan is the speaker, so please. Okay. You can start the presentation. So thank you for being here. The floor is yours.
Okay, so good afternoon, everyone. My name is Yu Yuan. I am now a PhD candidate from Politecnico di Milano. It's a really honor for me to be here to introduce a recently developed novel measuring strategy specifically on measuring arches on behalf of my colleagues, Dr. Stockdale and Professor Milani. And since I am also having the presentation for the next one, so I think maybe it's better I combine the two speech together, because the contents I brought up in the second presentation may answer some of your questions from the first one. So I'll do this two continuously, and so you will maybe have a long speech. Sorry for that. And today, as we already see a lot of cases. So these 2 days, we know how important non-destructive testing approaches can be important for the field of civil engineering. Not only as important when we try to get an accurate measurement result in a lot of experimental campaigns, but also it can be a huge help when we apply the structural health monitoring on buildings. And among these non-NTDs, vision-based methods are very appealing for a lot of reasons, because such as it's fast and it's non-direct contact. And here we proposed an approach that is falls into this category, but not exactly the same as photogrammetry or DIC. It was designed specifically for based on the mechanical movement for a masonry arch. As we can observe for most dry stack masonry arches, the typical failure of the arch can be formed by 4 joints. So we will have the rigid body movement between the 2 blocks, and we were applied a certain patterns around the block joints, so we can describe and measure the movement of the blocks in a hugely reduced data amount compared to DIC or photogrammetry. And as we know, if we want to apply these approaches for long-term monitoring, the cost of both economy and human efforts can be greatly increased. And that's the original idea of why we want to propose this type of methodology to combine our knowledge as a civil engineering into the field of health monitoring. So today I will introduce first of how we realize this strategy, about some math and some MATLAB code we've implemented. And the second big part is about the validation of how we make sure this method is accurate in both the values of the measurement and also in the accuracy of identifying the mechanical joints formed in the arch. And since we have a lot of data during this, so I have a second presentation about a small GUI interface developed in MATLAB to storage and present the data and also give us some interesting phenomena regarding this kind of test. And finally, we applied this method in a series of experimental campaign to study the capacity of a full-scale arch under a tilting plane test. Okay, so first is about how this strategy was realized. First, we need to know if we have 2 blocks, it's obvious we can have 2 movement can slip, or they will have this kind of rotation. And with the combination of the 2 movement, we will have an 8 movements in total. And in our strategy, we will apply 16 points like this around the joint. They were perpendicular and parallel with respect to the central joint line. And we will name the original length with L and the deformed length with a single rotation or single slip with 1 apostrophe, and the combination of the 2 deformation with 2 apostrophe, and with a relative relationship between the deformed lengths between the row dots, we can classify our 8 deformation type. Also combined with the inclination of these points, we can know if it's a left slip or a right slip. And after knowing which type of this deformation is, we can calculate the exact value of this deformation. The first is the rotation. We can, as shown in this figure, we can calculate it with the vectors, the dot product of the vectors formed by the dots, and to get the angle. And as you can see, we have a lot of dots for the combination. For example, we can use the dots from the first row and the second row, or the first row and the third row. So that's what we do here. We choose only 2 points to form the vector. So we have a combination of a lot of these dot sets. And this redundancy will provide an extra accuracy for the calculation, because we will repeatedly to get the same angle we want, but we repeat it so many times, and it was greatly improved the accuracy of the measurement. So also we can have several approaches. First is we to directly calculate the angle from it's already like this. After it's deformed, we can calculate it from the original position and the deformed position. We will plus the left one and the right one together and get the angle of this. And another way is we can directly calculate it from the deformed shape like this. We can have the vectors formed by the row, and also we can by the row. Also, we can get the vectors from the points formed by the column, the blue line and the orange line separately. And for the slip, the calculation approaches are more directly. It's just using the triangle rules to get the length formed by the original and the deformed points. And for the combined situation, since we know the dot products won't be affected by the position of the vectors, so we can adopt these advantages and to separately calculate these two situations. So to calculate slip first, then to calculate the rotation. And as I mentioned earlier, we can use the redundancy to greatly improve the accuracy. And this is a flow chart we've developed to determine and calculate the value of the deformations. It's maybe not really clear, I think, but so this part is first we get the length of all the deformed dots, and then we go to the judgment to see if it's a slip or it is a rotation or it is a combination of the two. And for the slip, as I mentioned, we can use the dots from a lot of different positions. We will have 16 values in total, and to get the average value. And for the rotation, we can calculate from the initial and the final configuration to get average value from the 16 combinations, or we can get totally from the deformed configuration. For the column pairs, we can get a 144 values. It's like a 12 plus 12, and for the row points, we can get 16 values. As together, it's 161 values we can gain for the rotation angle. And to already have this theory, we will see how it works. So the first way we choose here is to validate this approach via a photographic image. We draw this figure in, say, the AutoCAD, and we know the exact value of this opening is 10 degrees. And also the slip is one, if you can, it's not clear here, but we get all the 8 deformations. The slip is 4.3 centimeters, and we took 3 sets of photos from the overhead position, like this one, and the left skew position, like this one, and a downright diagonal skew position, like this one. And we do some not really complicated photo treatment, which can be realized in MATLAB. We can extract the dots, binary images of the photo like this. And to transform the photo to the data we want, we need to also do a set of a procedure. And it's called homography. The basic idea is we know the position, exactly the original position of 2 points from the photo, and we know it's how it should look like in the realistic world, so we can use it to project it to the coordinates we want with a matrix. And this matrix can be easily constructed by a MATLAB function. It's already there, so you can just use it. So the only thing we need to know is the exact position of the 2 points in the real world, like in the how you printed it on your paper. And so we can get the coordinates in the computer and to calculate the values and the of angles and slips. And here are the results for all the different combinations of the deformations. We can see the error is within 200%, which is, I think it's quite satisfied. And the time for running this code is not that long. For the combination of the rotation angles, it may take longer, and the total time plus is near 1.8 seconds to treat one set, like the 6 points of the 16 points of around the joint line. So it's not too much, and it's acceptable if we want to do a real-time monitoring in the future. And the second approach is to do the validation is more related to arch form. Here we built a small arch, a scaled arch with 11 identical blocks, which were 3D pointed and filled with the clay. And also we put the sandpaper on the side of the blocks to prevent the slip. So it's control it only to do the rotation, which will be easier for us to analyze in the preliminary verification of these approaches. And we do 6 tests in total, 3 from this point, this front wheel, point A, and 4 from point A, and each from point B and C separately. And this test doesn't last really long. For each video, we were recording it by a cell phone camera. It lasts about like 30 seconds to 1 minute, and the frame for each second it is a 30 frame for each second, and the movement of the failure of the arch is triggered by the movement of the left spring, manually controlled. And we have the video to record the full failure of the arch. And here to treat the data, we developed a small MATLAB GUI, which I will introduce to you later. But trust me, it's not too complicated to use it and to find the exact position of the frame you want. For example, I choose the rotation angle. For example, this is test 1. I choose the rotation angle of joint 6, which is the blue line here. And these 2 figures are the movement of all the 10 joints of both rotation angle and slip. And we can see this blue line is the only line with the deformation. So we know the joint 6 is a mechanical joint. And we want to know why, how is it moved? Is it a slip or is it a rotation angle? So we can see the more detailed results of this angle. This one is the rotation. We can see the blue bar is an arrow. We can see it is constantly goes up with little arrow, but this one is a slip. It also goes up, but with larger and larger arrows, which means this is not the answers we are looking for. It's wrong. That's why it has the arrow bigger and bigger. So we can make sure this joint were under the deformation of a rotation rather than a slip. And we can see for all the 5 tests, we exclude the test number 5 because it's from a skewed position. it's hard for us to measure from the photo ourselves, which is the rotation angle of the joint. So we can see the calculated rotation we extracted from the results is around 10. And here is the angles we measured manually from the photos ourselves. The error is also not too big. And the last part is we did some, we applied this strategy into a full-scale arches to study the capacity of a masonry arch under a tilting plan. So this arch was built by a wood board with the steel bars to simulate the masonry blocks. And we used a strap. So when the strap is closed, it's continuous, and you can see here it's not continuously. We use this to simulate the joint line. I mean the next presentation is also mine, so maybe okay, sorry. And we use it to control the happening of the mechanical joints. And we can see here the configuration, and we're lifting this plate higher by higher until the arch fails. And the test was recorded by a camera in front of it. The distance and the position are not recorded since they're not important according to our previously methodology. We can always get the relationship between the real one and the photo. And here is after we get the video, first we need to do a frame treatment. We won't do it for each frame. We will create a mask, and it will automatically to get this kind of figure for each frame. So we will set our threshold for the color, and also after we get the binary images, we will exclude the undesired noises such as the trees and the floors and other stuff by the specific configurations of the blobs, because we know the blobs we have have a pattern. They're 16 together, and also they have a specifically size compared to other noises. And so here is an example of how we do this for a whole arch. The blue points are the tracking points we used in MATLAB. It was masked on the original photo. So the way of doing it, after we get the photo from the photo to the binary images, we have to numbering all these sets and restore the coordinates of them into the matrix, and we will tracking these points by a approach called the minimum assignment cost, because we know for each frame we have 25 frames per each second, so we know it moves really slow from frame to frame. And when we try to track the minimum distance of the points close to, so because for example from the first frame is here, and the fact for a second it is only this close. So to track to get the minimum cost, we can locate the next position of the point we are tracking. And also sometimes we will meet the problem such as we will lost some points because it may be errorly limited as a noise, but it's not a problem because as I said, we have a lot of frames per 1 second. For this test, the arch fails in 2 minutes, but for a longer health structure monitoring project, we can even maybe track the point maybe within 1 minute or even 10 minutes because it doesn't move this much. And so this is not a problem. And after we get to know the exact point of the centroids of these blobs, we can calculate the deformations as I introduced before to identify if there is a opening or a slip and to get the exact value. And here is the result for this example. I have to point out that we don't use the rotation angle and slip for the long-term monitoring because we have to calculate. Though it's really fast, but you still have to take up your computer and also your time. So now here for the long-term monitoring, we are choosing the two indicators of the length between the inner point sets and the outer point sets. But remember, we have 4 rows. So we will do this inner one and the outer one. When we see there is a big maybe movement or something, or a continuously increasing of the value, we will activate to calculate the rotation and sleep. So this is another way to save our computer resource, making this approach very cheap because we only have several points we have to store the data, and we don't actually activate it to starting the measurement and calculation before we noticing there is a move up of this joint. And we can see the 4 joint values we determined from this approach is exactly the same we set in our experiment. And another point I want to stress is about the noise. We can see it seems like a lot of noise, and that's because when we are using a camera, we don't have to use a high resolution camera because we want only to determine the centroids. So this is a point we have for the full-scale arch, and this is a point we have from the earlier small arch, if you remember. So since that one is more close range, so the points are more clear, it has more pixel, so it's more easy for us to determine the constant centroids of the blobs. So for this one, the errors can be large, but still for long-term monitoring, it's not a big problem, and you can see the trends even with this noise. So for a conclusion, I think we can see this is only a preliminary methodology for a long-term health monitoring, but it still can show the advantages such as it's really fast, it's cheap, and it doesn't require a lot of, like for DIC, maybe you have to position your camera in a fixed position and you want the lighting condition to be constant during experimental test. But for this methodology, we don't ask this. And also it's generally applicable for the movement between the rigid bodies, maybe not only bridges. We combined with the specific movement of other masonry structures, we can adopt it into other type of structures. But also we can see there are limitations, obviously. First is like the noise, and we may reduce it with other more refined treatment during the tracking. This is the future task we want to resort to. And also this is not applicable if we were having plasters on the surface of the bridge because it doesn't show what's happening inside. So, and also maybe in sometimes we are not allowed to put these points on the surface of the bridge. This is when maybe we can use some infrared tracking points to replace this visible black dots. And for the small GUI I've mentioned earlier is here, and we.
Okay, so this is the other works, no?
Yes.
Okay. The title is Interactive Software for Behavior Mapping of Masonry Arches. So this is shorter than.
This is much shorter.
Well,
it's only.
Well,
Thank you.
The floor is yours.
So this is a GUI interface we developed in MATLAB to storage the data we've obtained with this scale arch test. And the aim of this GUI, as I said, it's storage and the present. Also, it have some educational purpose for some maybe students or someone who is interested in the behavior of arches who might not be familiar with the mechanical movement of these rigid blocks. And this is the interface of GUI. It has 2 windows. This one is to show the videos we recorded during the test. And this one is to show the data, the results we calculated. And here we can choose the type of data. We can choose the rotation angle, the sleep translation, and also the length between the 2 sets, as I mentioned earlier. And here we put all the six test inside the GUI already. And here is an exact value of the deformations of all the 10 joints. And here is a slider. You can choose the position you want to go with the frame number. When you switch the button to play, it will automatically play. And if you want to stop at a certain frame, you can switch it to the pause, which is really simple. You don't have an educational tutorials, I think. And the interesting point is when you click the joint button, it will go to the interface like this to show the data of one exclusive joint you are like. In the first one, you can see all the joint. It helps you to recognize which one is maybe have some movement. But this one is for you to see if it's the real deformations you want. And here is, as I mentioned, how you can determine if it's a slip or a rotation. Here we can see, we know something happened for the joint 6, but it's not slip because it has a bigger and bigger arrow. It's a rotation. And here is the example of how we can determine the movement of the happening and the failure of this configuration of these arches. We have this sliding over this foot because we applied a manually sliding to trigger the failure of the arch. And when there is 2 joints on this arch, it's still stable. I think it's the basic knowledge of the movement of the rigid part. And we can see for some figures, we cannot recognize 2 movement. That's because the second one is actually at this position, because we don't have another 8 points around the basement, so we cannot record the movement of the first joint. And also to know that we can always scale the images in the MATLAB GUI, so you can see really a lot of detail of this. And here are some interesting things we can recognize with this the video with a lot of data. For here, as we can see, there is a really small rotation of this blob. It may only happened like less than 1 second. It's only several frames, but it can be recognized by these curves, give us the potential of how this sensitive can this methodology to be. So can give us a lot of information you cannot observe by your eyes. And also here give another example, interesting, because for this joint, we can see it first goes down, then up. It's weird because if it's opening, it should constantly go up, the rotation angle. But here is no. Also, this happened for in test 3 as well. This is after we checked the video and also the experimental blobs we are using, because we found for the manufacturing default, joint 10 is originally not closed. So the rotation is firstly closing the joint, then opening in another direction. And for conclusion, this GUI is small, but it's useful. And also it has the potential to adapting it into another configuration of the arches, such as we also did this one for the bigger one. We can also put all the joints data here. So it may have the potential to combine with our introduce the methodology for a long-term health monitoring platform, maybe in the future. And that's all. Thank you. If you have any questions. Okay, thank you.
Okay, thank you for these 2 presentations. So I ask if are there any questions about the 2 presentations that you have presented? Okay, no, I have just a question, and I want to know if this technique can be extended for monitoring also out-of-plane displacements and deformation, and in which way, if yes?
But now it's not. You have to apply the dots on other face. For this is only for this face, so I can only calculate the movement inside this surface. But if I want to get this one, we have to apply the dots in another surface of this structure. Okay. And I think this can also combine. I think it's always recommend to combine one technology with another one, because maybe they have their own strengths. For this one, it was specifically designed for the rigid body movement between the blocks, and for the outside of plan, maybe it's better to use some maybe laser or other. We have other cheap methods to use.
Okay, just another curiosity. In order to enhance the accuracy of this innovative technique, it can be a good strategy, a good solution to increase the number of cameras and interpoling the results, no?
Of course, it can be, and because you have two positions, maybe you can repeatedly calculate it to reduce the redundancy. Not to reduce the erroneous, but the point we developed is because, as you can see, we can use one single camera, which doesn't require high resolution solutions, which means we can monitoring a bridge just using a security camera or the CCTV on the street to monitoring some structures. So this is kind of like the strength of this approach. Surely you can use two, but it also will double the efforts when you calculate. But as far as the accuracy we get now, we think it's quite satisfactory with even one camera for now. It's only a preliminary test with not a complicated movement, but in the future, I think maybe, yes, it will be helpful.
Okay. Thank you again for these two presentations. Okay, now the next work is done by Domenico Camassa, myself, Anna Castellano, Aguinaldo Fraddosio, Michela Silla, and Mario Daniele Piccioni. The work is titled Ambient Vibration Test of Historical Masonry Bridge by means of radar interferometry. So I am the speaker of the presentation. Okay, so historical masonry bridges are a testimony of our past, and their importance lies not only in the strategic role they play, but also in their cultural and architectural value. Recent catastrophic events, however, have shown the high vulnerability of these constructions. Therefore, in order to preserve this heritage over time, it is necessary to apply prompt and appropriate conservation actions. In this context, ambient vibration testing can be very useful. This testing technique starts from measuring ambient vibrations of a structure, namely vibrations due to wind, traffic, etc. And then by applying operational model analysis method, like the FDD method or the SSI method, model properties of the structure are extracted from the measurements. Model properties such as natural frequencies and mode shapes. So in general, ambient vibration testing is very useful in structural analysis and structural assessment. Indeed, model properties can be used for several purposes, such as models calibration and damage characterization. Moreover, this testing technique can be applied in operative condition, is non-destructive, and among non-destructive technique has the very appealing feature of monitoring the global response of structures. For these reasons, ambient vibration testing, initially developed in the field of mechanical and aerospace engineering, is now also spreading in the field of civil engineering, and also for application for the conservation of historical masonry bridges. So in particular, in this vein, several applications exploit this testing technique to support structural vulnerability assessment and the design of retrofitting interventions. Now, usually in ambient vibration testing, structural vibrations are monitored by means of accelerometers. Even though these sensors provide very accurate measurements, they need to be installed at several points of a structure and to be cabled. So they require full access to the structure, and their installation is time consuming. This issues, unfortunately, in the widespread use of ambient vibration testing for large and massive masonry constructions like historical masonry bridges. So in order to overcome this problem, new measurement techniques have been proposed. And one of the most interesting and emerging technique is the ground-based radar interferometry. But what is an interferometric radar? It is a coherent radar expressly designed for measuring displacements and vibrations at several points of a structure. The working principle is that of sending electromagnetic pulses, which are reflected by a target and come back as an echo. Then the capability of measuring displacement is based on two special techniques. In short, the stepped frequency continuous wave technique enables range resolution. Using this technique, the scenario illuminated by the radar is discretized into resolution cells, named range bins. So since reflected echoes should have a sufficiently high signal-to-noise ratio to be useful measurement, it is very important during data acquisition and data processing to consider the range profile, namely the plot of the signal-to-noise ratio of echoes received from each range bin. Then, once the scenario has been discretized, the interferometry technique allows for determining the displacements from each range bin. Basically, when a target moves, the echoes reflected in two consecutive acquisitions present a phase shift. So by measuring this phase shift, the interferometric radar determines through suitable mathematical relation the displacement of the target along the line of sight direction. So in comparison with the accelerometer, the interferometric radar has many advantages, and in particular, it requires no contact, and so it requires no access to the structure. It is a very important advantage. Also, it can simultaneously measure displacements at several points of a structure from the same position. Its installation is very fast, about 15 minutes, and it has good accuracy, up to 0.02 millimeters. So microwave radar interferometry, which has been successfully used for ambient vibration testing of slender masonry constructions like towers and bell towers, can be very promising also for applications on historical masonry bridges. But nevertheless, to our knowledge, very few works in the literature have explored the capability of the interferometric radar for characterizing the dynamic properties of historical masonry bridges. The main two works that we have found in the literature are those here represented in the slide. In particular, in this work, an interferometric radar was used in a multidisciplinary approach for conducting force vibration tests on a severely damaged historical masonry bridge. And in this work, an interferometric radar was effectively used to assess the first natural frequencies and the dynamic impact factor of a railway masonry bridge. So, given the limited work on this subject, the purpose of the present study was to explore through a case study the possibility of using the interferometric radar signals for identifying the first natural frequencies of historical masonry bridge. With this aim, we have carried out several ambient vibration tests on the historical masonry bridge named the Lama Monachile Bridge, which is located in Polignano a Mare. And in particular, we have carried out ambient vibration tests both using the interferometry technique and the accelerometer technique. This last one has been served as a benchmark technique. In all these tests, the bridge was subjected only to ambient excitations, in particular to wind and pedestrian traffic. Now let's see the accelerometer test, the benchmark test. For this test, we have installed 20 high sensitivity uniaxial piezoelectric accelerometer on the deck of the bridge. The measurement layout was expressly designed in order to detect both flexural and torsional modes of vibration of the bridge. And then the frequency domain decomposition method was applied, and it allows to determine the 3 modes of vibration of the bridge from the measurements. In particular, the first mode is a lateral bending mode with a natural frequency of about 7 Hz. The second mode is a torsional mode with a natural frequency of about 11 Hz. And the third mode is a vertical bending mode with a natural frequency of about 16 Hz. Now, let's see the interferometric radar test. For this test, we have used an IBIS-FS system as the interferometric radar. And here, for the sake of brevity, here we show only the results related to just one of the 3 interferometric radar tests that we have conducted on the Lama-Monachile bridge. And so in relation to the test that I want to show, in this slide, it is represented the relative position between the bridge and the interferometric radar, here represented schematically as a green sphere with a semi-transparent cone of view. Range bins, namely resolution cells, are also represented as slices on the bridge within the cone of view. As it can be seen from the image, just a narrow portion of the bridge, this one, that this in the cone of view, was monitored. In this way, it was possible to reduce the ambiguity measurements due to the lack of azimuth resolution of the IBIS-FS system. But despite such precautions, 2 other problems arise. The first problem is that the interferometric radar is mounted on the top of a tripod, so it can vibrate, thus corrupting the measurements. For this reason, according to some works in the literature on the interferometric radar, we have installed on the radar head a uniaxial piezoelectric accelerometer in the direction of the radar antennas. In this way, it was possible during data processing to remove the vibrations of the tripod from the interferometric radar measurements. Now let's see the second problem that arises. As it can be seen in this image, the cone of view of the interferometric radar also includes the metallic balustrade, which reflects electromagnetic waves. So this reflection could be a dynamic cluster for measurements. So to avoid this problem, we have also carried out some preliminary vibration tests by repeatedly striking the balustrade and measuring its vibration through the interferometric radar. In this way, indeed, it was possible during data processing to determine the natural frequencies of the balustrade and distinguish them from the natural frequencies of the bridge. So let's see data processing and results. The first operation that we have conducted was removing vibrations of the tripod. Specifically, the signals recorded by the accelerometer fixed on the radar head were properly processed and then subtracted from the interferometric radar signals. Then the frequency domain decomposition method was applied to these signals. And now by analyzing the plot of singular values of the spectral density matrix of those signals, it is possible to detect the presence of several clearly visible peaks. Specifically, up to 12 Hz, there are 6 sharp peaks having the frequencies summarized in this table. But not all these peaks, however, correspond to natural frequencies of the bridge. Indeed, as I have just said, those peaks includes also natural frequencies of the balustrade. For this reason, we have also analyzed the signals acquired in the vibration test on the balustrade, from which it was possible to extract the first 5 natural frequencies of the balustrade. So by comparing the frequency extracted from the interferometric radar measurements on the bridge, here reported in this column, With the natural frequencies of the balustrade here reported in the second column, it is possible to recognize that the frequencies highlighted in red in this column, in the first column, are actually the natural frequencies of the balustrade. Indeed, the relative difference is lower than 10%. Therefore, we can deduce by exclusion that the natural frequencies of the bridge are only those highlighted here in green, at about 7 Hz and 10 Hz. Indeed, these two frequencies do not correspond to natural frequencies of the balustrade. Now, in order to evaluate the accuracy of this estimation, we have compared these two natural frequencies estimated with those extracted from the accelerometer data, which I recall served as a benchmark test. And as it can be seen in this table, the interferometric radar has been able to determine the first two natural frequencies of the bridge with a good accuracy. Indeed, the relative difference is lower than 9%, 9.1%. So in conclusion, the results have shown that by taking into account all possible sources of measurement errors, such as vibrations of the tripod and the presence of dynamic clusters, the interferometric radar provided the first two natural frequencies of the monitored bridge with a good agreement with the accelerometer results. Future studies will include carrying out other experimental campaigns, developing techniques for achieving a better accuracy in the estimation of natural frequencies, and implementing more advanced techniques for cluster removal. So thank you for your attention. Are there any questions, comments? Okay, yes, the mode shapes, no? Yeah, okay, this is a problem of the interferometric radar. Indeed, since the interferometric radar measure only the line of sight displacements, the component on the line of sight, it is quite impossible to, with standard testing, with interferometric standard testing modality with the interferometric radar test, to determine the mode shapes. So, and we have carried out some studies for this problem, and the solution that we have found, that is in that we have found, and we are researching, is to use simultaneously two interferometric radar. So in order to triangulate the displacement vector, and so determine the mode shapes of the structure. Maybe I think that with just one interferometric radar, it's quite impossible to extract mode shapes. Another solution can be also, if I know the direction of displacement of the structure, in that case, you can estimate natural modes with just one interferometric radar. But if you don't know the direction of the displacement, yeah, you need two or more interferometric radar. No, we have just one interferometer, but for example, in my PhD thesis, we have my PhD was in a caratterizzazione industriale, so industrial. I don't know how is the name in. Yeah, with an industrial partner, which provided the second interferometric radar. And so we have done some tests with two interferometric radar in order to prove, to validate the method that we have defined for determining the mode shapes of structures with 2 interferometric radar. Yes, also. Yes. Yes, indeed, knowing the mode shapes can be very important both for models calibration, for advanced mode calibrations, and also for advanced damage characterization. There are a lot of methods indeed that need to know the mode shapes and the variation of mode shape before and after the damage. Yes, so. Okay, thank you very much. Other questions? Okay. So we can conclude this special session, and thank you very much for the presentation of all the speakers and for the participation of the audience. And thank you very much also to the General Chairs, Francesco La Monaca and Gabriele Milani, and to the University of Calabria. So goodbye to everyone, and thank you again.